today, we will start with this concept of machine learning. What is machine learning? And it's become a dominant theme. Wherever you look, people say, oh, machine learning. The exploding number of jobs of machine learning, exploding number of applications of machine learning. It is hard not to find machine learning. People often use the term artificial intelligence interchangeably. So the question therefore is, what is artificial intelligence? It's sort of part of the zeitgeist. You hear it every day. You hear it in the news. You hear it in popular conversations. We all, irrespective of what walk of life we belong to, we have all heard the word artificial intelligence. We have heard the word machine learning, perhaps less frequently. There are movies about artificial intelligence and robots and whatnot, and obviously Terminator and so on and so forth. There's so much of fascination with this entire concept of artificial intelligence, right? So what is the relationship of all these things? Machine learning, artificial intelligence, robotics, all of these. We will today be a little bit more precise about what they mean. Right? See, the term artificial intelligence is a fairly, I don't know when it was coined, but it's been there for decades now. But it is a millennial dream of human beings. It's sort of older than any of the technologies we develop. You go and look at the mythologies of just about every civilization, and you will see an aspiration of man to be the creator of intelligence. To the extent that we believe that God created us in God-believing nations, right? We are created beings, we are creatures. There has also been an aspiration amongst human beings to create of their own forms of intelligence. For example, in just about every civilization that I can think of, for example, in Hebrew culture, there is the story, I believe is Golab is the word. You would make a mud doll and something like that, a figure, and then with the appropriate invocations, you could breathe life into that. And if you did, it would do things, it would do extraordinary things. In the Aladdin and the Magic Lamp, you again have this character who can do whatever you want. It's a creation. You just rub the lamp and lo and behold, there's this amazing magical creature that comes in. So people have aspired to create things of their own that are intelligent, not just dumb machines, not just steam engines and ships and planes and so forth, which they know are mechanical devices at the end of the day. Marvelous mechanical devices, but we all acknowledge that these devices are mechanical as opposed to intelligent. They exhibit no forms of intelligence. We have always wanted to create machines that exhibit intelligence. The first prototype of a machine, or at least the concept of a machine that could compute, was by Charles Babbage. I believe his design at that moment was ahead of its time. It could not be realized. We tried very hard to realize it couldn't be, until that it has been realized now, and it is there in the Technology Museum in San Jose, or the computing, I don't know, which museum is it? Museum of Computing? Yeah, computing history, right? So people have actually recreated that machine and found that it does actually work. So even before the computer, the first computer actually worked, the creators were dreaming not of using computers to compute per se, but to create intelligent machines. So creating intelligence machines has been a pretty long millennial dream of people. So today, I will ask this question: what is intelligence? When we speak of intelligence, what is it? Let us be more precise. Right? Now, intelligence, artificial intelligence, has many sort of definitions, and it has evolved over time. In the beginning, people thought they could create, they were pretty optimistic, they could create strong forms of AI, what are called forms of strong AI, strong artificial intelligence. They could actually create thinking machines. There was even a legendary company here in Silicon Valley literally called thinking machines, into which some of the great Nobel laureates like Richard T. Feynman, etc., came and contributed some excellent work. Those were great efforts. They didn't quite succeed. It turns out that that was too ambitious. Today, we have a more pragmatic definition of intelligence. We say that anything exhibits intelligence if it can learn. Are we together? So intelligent machines are not thinking machines, but learning machines. Machines that can learn.
And apply.
Together. And therefore, the theory of machine learning. Right? So now let us quantify what is learning. Learning is, how do you know that we have learned? Let's take an example. You take children to a zoo. Let's say you take some kindergartners to a zoo. In the zoo are all sorts of animals, but let us simplify it, and you show the children an animal, and you say, you know, this is a cow. And do you notice the horns on its head and the long swishy tail and the four legs, right? And the big size and so on and so forth. You express all sorts of attributes of the cow and you say, this is a cow. Then after a little while, you happen to encounter, let us say, a duck. And then you say, well, look at this animal. It's small, it's feathery, it has webbed feet and it has a beak, right? And this is a duck. And then the child is maybe trying to make head and tail out of what you said. Generally, adults say a lot more than a child can comprehend, right? So the children move forward, and after a little while, you show more examples. You say, that is a cow because this, and now look, that's a duck. And you keep on encountering different animals. And let's say in that meadow that you have taken, the part of the zoo or the meadow that you have taken your kids to, it's all cows and ducks. And you show all these cows and ducks. How would you know that the child has understood what a cow is and what a duck is? Learned about cows and learned about ducks. So one way that you could do is, as you travel, you can point back to the cow that you showed and said, what is it? And if the child says duck, you know the child hasn't yet learned, isn't it? But if the child says cow, you may be inclined to believe that the child has learned what a cow is. But there's a subtle flaw in this reasoning. Would anyone like to point out what the flaw in the reasoning is? Go ahead. Guesses, yeah. So you ask many such examples, very good. You ask many such examples and you look at the error rate, how often the child is making an error. If the child is just guessing, the error rate would be high, right? But there is one more subtlety. Suppose the child with fairly good low error rate can tell cows to be cows and ducks to be ducks, the ones that you have already shown the child. Would that convince you that the child has learned what a cow is and learned what a duck is and to distinguish between the two?
Might have memorized some feature.
That is right. The child may just have memorized those specific instances of it. Some people have perfect recall. They just remember. And they remember that this was cow, 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 duck, duck, duck. But the child has really not understood it, because when you show a cow that the child has not seen, the child is stumped. Or a duck the child has not seen, the child is stumped. So in other words, and therein is the crucial idea. Learning is the ability to generalize from data. Are we together? You generalize from the data that you have seen to beyond it, right? That is the distinction between learning and memorization. To make it very practical, all of you have been through the education system, right? Which can be, it can range from brilliant and absorbing and great professors to absolutely dreary courses in which pretty much make you hate that subject, right? So you have the whole range, and then we all have to somehow get through those courses. So the ones that you don't like, what do? Well, I can tell you from my experience in the IITs, what you would do is you would have something called the important questions and question bank in those subjects. So you would just have a question bank of about 40, 50 questions, right? And you just hated the subject. So the day before the exam, you would just go and perfectly memorize those questions and the solutions. And so should they appear in the exam or anything close to it appear in the exam, you would be able to solve it because you have just memorized how to do it, right? So, but as you would agree, memorization was not understanding. I had not learned that subject. I had just found a way around it by memorizing it and still getting a reasonably good grade to then put the course behind me. So that is the distinction between memorization and learning. Learning is the ability to generalize. You can solve a problem that is not there as part of your question bank, isn't it? You can solve new problems. That is learning. So that is machine learning. Now, artificial intelligence, these words are very often used in a broad sense. So I will just draw a picture. Suppose this is artificial intelligence. Then machine learning is the theoretical core of it. This is machine learning. Within the field of artificial intelligence, there has been other things. For example, the application of machine learning to all sorts of areas. For example, you apply it to robotics. Examples of robotics are your gazillion examples. For example, your self-driven car, right? Your Roomba, your this and that, your vacuum cleaner these days. And it's hard to point out places that you don't have. So this is the theoretical core. Theoretical core. Now, what happens is that within machine learning, there are many, many algorithms. One class of algorithms that has gained considerable popularity these days is deep neural networks. So let me just call it DNN, deep neural networks. And I will just call it here a deep and in this world, there are many things like SVM here and ensembles. There are countless jewels in the world, in the theoretical world of machine learning. There are literally countless jewels, marvelous, wonderful jewels. One of the jewels is deep neural networks that is very much in vogue these days, especially for unstructured data, especially for images, sound, and text. These are unstructured data that is not tabular or as a spreadsheet. For deep neural networks are very effective. And deep neural networks occur. These are also known as deep learning. Deep learning is an interesting word that they have latched on to, actually. Hats off to the marketing genius of whoever gave the word deep learning, right? Because it somehow looks very deep, isn't it? But it is yet another class of algorithms within the machine learning world. Now, one of the abuse of terminology that is happening these days, and in fact, many companies are culpable, is that they tend to equate artificial intelligence with just deep neural networks or deep learning, right? So they will, I actually have sat through some client calls in which they're saying, yes, machine learning everybody is using, but are you doing AI? Right? Right. So you see the absurdity of that, but it is because these people are not technical. And it is partly the fault of the marketing from companies is that people have given the buzzword AI to deep neural networks or deep learning. Right? Quite often you say, oh, I'm doing AI, I have run neural networks and so on and so forth. So it's sort of a part of the abuse of terminology that's happened. But this is the real picture. This is the relationship of all of this. So this is machine learning.
In terms of framing, why would you put robotics completely non-intersectional?
Oh, no, I should not. I should not. I should not. These are all, this feeds this. Feeds this, let's say.
So Venn diagram, they should overlap.
Yeah, yes. The way I would look at it is machine learning is the theoretical core. Robotics is the implementation that uses a theoretical core, the actual mechanical implementations, because there's a lot of mechanical engineering and other things that come into this, right? So that is that. So this is a broad sort of a relationship. Don't take it very literally, but think of it as a containment hierarchy. Artificial intelligence contains many areas. The key areas are machine learning, robotics, etc. There used to be expert systems, but we don't talk about that anymore these days. Then within machine learning, there's a large number of algorithms, absolutely wonderful jewels. We'll start with one today. So one of the jewels that is very much popular for unstructured data these days is deep neural networks or deep learning, right? So, and we'll learn about it. But this particular workshop, this data science workshop, will predominantly focus on, at least in the first part, on structured data, on tabular data. Right? We will have occasion to learn deep learning at the very end, little bit, but there's an entirely separate workshop we run dedicated to deep learning, for which you're invited. Right. All right. So with that relationship out of the way, I would now ask this question: learning. When we say that machine, like generalization from data is learning, how do you quantify it? Ultimately, it is science. We're talking about, we are engineers and scientists. For us, things have to be measurable. So what is a measure of learning? Right? So let me pose this question here. What is the measure of learning? Learning, this is the crucial question. We don't know how to quantify thinking, so we could never create thinking machines. But it turns out we can quantify learning. So let's go back to the story of the children and the teacher in the meadow or the zoo. Now, you ask a child, let's say one child, you keep showing and explaining the cows and the ducks. And in the beginning, the child doesn't know. So the child is guessing. So when you show it an instance of a cow or a duck, it will guess. And you would observe that the child is making a lot of mistakes. So you can count the errors. Count, quantify, errors. Let's say that the error is this, right? The amount of errors you make is this. Maybe out of 100 samples, the child is getting 30 samples wrong or something like that. Okay? But when would you begin to get the feeling that the child is learning? When the errors keep coming down, isn't it? The child is able to identify most of the cows and ducks correctly, because that would be a measure that the child is learning. Are we together? Right? So learning is the simple idea, I hope is clear, because this is the heart of it. Learning is a reduction of measurable error. Learning is the process of the errors. Right. In the prediction errors, like what is it? Is it a cow or a duck? It's the process of systematic reduction in the errors. This is it. So what is the problem? Whenever we create a machine or an algorithm, in the beginning, it will make certain errors with the data, and then it needs to find a way to decrease those errors. So those are the two legs of it, errors. Now, so we need in machine learning two fundamental things, two mental quantities, two fundamental things, let me just say. One is a quantification of error, E, right? It is also called the loss function. Let's remove that, E. And the second thing that you need is an efficient and systematic way to reduce the errors. Error E, isn't it? To reduce the error E, or the word that you use is minimize the error E, right? And so your model is, and I'll just use, let's say that of all the possible hypotheses that you can make explaining the reality, that hypothesis is true, which produces the least error in prediction, right? So all of this, we will make it much more concrete as we move forward now, right? So an efficient way that we will learn, I will just throw a word here for future reference, but it should mean nothing to you at this moment, is one of the efficient ways is gradient descent. That is pretty much at the core of much of machine learning, often used for this purpose. We'll see that today. So two concepts that we will learn today is quantification of error and a systematic way to reduce the error, right? So let's take a real example with data. Suppose I take this example. Consider an entrepreneur, a young entrepreneur, is the spelling correct? Entrepreneur, E-N-T-R-preneur, selling ice cream on a beach. So suppose you want to open a shop and sell ice cream on a beach. Now, this is a toy example, so take it in a lighter way. Don't super analyze it. So the point is to just frame something we're going to learn. So when you want to sell, you want to open an ice cream shack on the beach. Ice cream now is a thing that has a very short shelf life, isn't it? It's a perishable item. You go to the dealer, you buy a few buckets of ice cream, a few gallons of ice cream, and you better sell that ice cream by end of the day, most of the time. Let's say that it is, because ice creams don't last long, especially, I mean, it's just has a very quick expiration date. So now you have a problem. You have to estimate how much ice cream you would sell on a given day before you go in the morning and purchase ice cream in bulk from the dealer, isn't it? If you purchase too little, then you will have a lot of customers who you'll turn away, a lot of kids that you will turn away because you would have run out of ice cream. Not a happy situation to just sit there and watch all the kids going to the other ice cream shop, right? As an entrepreneur, you would be pretty sad about it. On the other hand, if you buy too much ice cream and you can't sell it, well, that's a loss, isn't it? You paid money for something, good money for something, and it went to waste. Therefore, you have a motivation, real world motivation, to predict how much ice cream would actually sell on the given day. So let us say that the amount of ice cream that sells on a given day is a function of temperature. Whatever is the outside temperature, let's say approximate outside temperature, the average temperature of the day or the noon temperature, or pick a value, a temperature at a given time. Whatever the temperature is at a given time, you realize is a good indicator of how much ice cream you'll sell. Out here in Northern California, that's a pretty good predictor. If it is a cold day, nobody will come to the beach. If it is a hot day, lots of people are on the beach and they have their families and so forth, right? So there are multiple factors. For example, whether it's whether weekday, holiday, or a work day, right? Even on a nice, pleasant, hot day, because it's a weekday, our parents are not free to bring the kids to the beach. So you may not have many people. So there are many, many factors that we'll consider. But for now, we'll take only one factor. Let's take temperature as the factor, right? So we will say, let X be, let us make data, plot of the data, X, which is temperature. And we'll hypothesize. Remember, it's a hypothesis. We'll look at the data and we will hypothesize a relationship. We will say that ice cream sale is a dependent variable. This is the independent variable. This is often called the predictor. Dependent variable, depending upon which literature you're reading, independent variable, independent, not independent, independent variable, predictor, regressor, input, and so forth. There are many names for the basic X, right? Driver, essentially. And based upon which tradition you're looking at, statistical or this or that, there are a lot of different traditions that have contributed to data science. And the Y is often called the target variable or the response variable. It is also called the regressand or the dependent variable. These are all synonyms. And these are all synonyms. In various literature, you use different words for this kind of thing. So now let's look at the data. Here's the big mystery. How does the data look? Let's say without some data point, I will take, suppose data looks like this. And I'm taking a very simple hypothesis. I don't believe the real world may look like this. So this is sort of a contrived way of putting it. Suppose your data looks like this. Each of the points is a data set. So what the entrepreneur has done is taken a methodical approach, seen how much ice cream sells on every given day, or maybe bought that data from somewhere, I don't know, one way or the other, has acquired this data. And this data, you look at it, and you may hypothesize, looking at this, what do you see? Do you see a positive correlation, negative correlation, or no correlation at all? There is a direct positive correlation. A direct positive correlation implies that there's a linear, obviously there's a linear relationship implicit here. So you would like to imagine that Y seems to be proportional to X, right? The amount of ice cream you sell seems to be proportional to the temperature. So you might want to posit a linear relationship. Based on that, you may hypothesize, for example, that Y is equal to, what is the equation of a straight line?
Y equal to mx plus c.
Mx plus b or c, depending upon which textbook you're reading. So this is your slope. This is your intercept, right? Just as a recap, what is a slope? The unit rise of Y for every unit increase of X, isn't it? If you increase X by 1 unit, how much does Y increase? That is slope. How steep is the line, right? And intercept is where exactly, when X is 0, then how much is y when x is 0? That is your intercept. Right? Now, remember that this equation, which we learned about in our high schools and so forth, we will just reframe it in based of our Roman and Greek thinking. So is y a measurable? Is the amount of ice cream that you sell a real measurable? It is, right? As an entrepreneur, you would know how much you sold, isn't it? So y, we can keep a Roman letter for it. Let us rewrite this equation. Slope, is slope something that you can see? Is it an observable? Sorry. Is it an observable slope? No, it's a concept. So we will give it a Greek letter. And how about intercept? Also a concept. So typically, and this textbook of yours uses beta and beta 1 x. This is nothing but your b slope or whatever you look at it. And this is your, oh, sorry, not slope, sorry, intercept. Sorry, I apologize. Intercept. This is your slope. Are we together? Your m in the previous equation. If you try to compare this equation with this equation. So far, so good, right? All we have done is rewritten the same thing with a slightly more standardized notation that is common in the machine learning literature or the data science literature. Now, whether you use beta or you use something else, another thing that you often find using, in fact, I'm much more familiar with writing it like theta naught plus theta 1 x. Is it any different? No. I just replaced the Greek letter, one Greek letter with another. Instead of using beta, I'm using theta. Yeah. Also a common. But observe one thing, these are equations of a line. So what we are saying is there is a linear relationship between x and y. It's a line relationship. But when you look at the line relationship, right? So let me draw the perfect line here. Well, as straight as I can be. This has some value of beta naught, beta 1, isn't it? A unique value of beta naught. But you also notice that y is not exactly, any given y is not exactly sitting on the line. The real data has a little bit of a, what does it have? A gap. And this is your difference between, it is called the residual. The gap between reality and prediction, right? So we will now refine a convention by saying that what you predict points on the line, like for a given value of x, given value of xi, this one is yi, the reality, and this one is the prediction, yi, and predictions traditionally in machine learning wear a hat, right? You make the predictions wear a hat just to distinguish it from the actual observable, right? Y hat.
So what we are going to predict is going to be on the line, right? Or no?
Yes, because if you make a straight line model hypothesis, the best value that you can predict for a xi value for a given temperature is that you will sell this much of ice cream on the line, isn't it? But your data says that actually you sold yi. So there is a gap between xi and yi and yi hat. So that brings us to the concept of a residual. Residual error. The word is residual error. It is for a given residual error for a given data point I is equal to yi minus yi hat, right? It is the gap between the prediction and the reality, right? Obviously, you want to keep small residuals. Go ahead.
So is that y the first one? Or is that a hat?
You mean here?
Residual error, the First one, yi is equal to
Epsilon I.
wait,
The one in the box, Asif, that's epsilon I.
Oh, this one, right? Yeah, you can. So people use different letters for it. People often use the word epsilon I, and sometimes in your book you use the word Ri also. Your textbook often tends to use little Ri. Obviously, epsilon I is a bit more clear. It's the residual error. Now what happens is, now comes the learning part. So far, are we clear? What is a residual error?
So
Right.
it can be both positive, negative.
Yes, in fact, it is. So for example, let's take another blue point here. Let me deliberately exaggerate and put a point here. So let me take this point, xj. For xj, you notice that this is yj, the reality, and this is yj hat, isn't it? And so y minus yj hat would be a negative amount. The residual would be negative.
So Asif, so what we are saying here is when we go from 1 to n, our residual, if it is close to 0 or 0, then we have a good model.
No, what we are, no, so we are developing the intuition. You are there, almost there. There is only one catch to it. See, you have lots of data points. For every data point, your model is making some error. You want all the errors to be in some sense small, the cumulative error to be small. Are we together? Now the thing is, how do we define from this picture, how do we define the concept of a cumulative total error of the model? What we want is total error of the model or the hypothesis. Model is nothing but the hypothesis. The hypothesis that you made. Every time you make more realistically, the line, the specific line is your hypothesis line with a certain value of slope and intercept is your hypothesis. Now, what is the total error? This is what we want. So one way that you could do is you could say, hey, you know what? Maybe I will take, can we use this? So the question is, can we use E is equal to sum over, like basically, I will first use a more compact notation, sum over all points of epsilon I. Just add them up, which is equal to epsilon 1 plus epsilon 2 plus epsilon, all the way 3. Can we use this? Can we use, think about it. Can we just add up all the errors to get a total error?
Yes, because there will be some negative, some positive.
But the problem is they might become 0. The sum might be 0.
Well, that would be a good situation to be in, right? Eventually.
Well, let's think about that. I'll give you a situation. Let me contrive another hypothesis. Consider the hypothesis. Okay. Consider this hypothesis. And again, I'll use the same data point. I hope more or less. Suppose you have this data point, but now consider this line as a hypothesis. I hypothesize that I mean, this is just some line, hypothesis H. Would you consider this hypothesis to be a good model for your data? Because see, all the negative, for every negative, I can find a positive residual. Isn't it? For this, I can find this. So if you look at it, the error, the total error would be close to 0. But something tells you this is not quite a good model, isn't it? It is not as good a model as the previous model that we built, the yellow line model that we built here, isn't it? Raman, do you see that?
Yes, I do. Yeah, I'm trying to
So
think.
now we have a problem because just adding up all the residual errors is not a very good idea. But then we look at the fact and you say, you know what? It is the magnitude of the residual that matters, not its sign. The pluses and minuses cancel out. But if you just take the absolute value of the residuals, perhaps that's a good idea, isn't it? Because those would all be positive quantities. And if you notice, the residuals, if you just took the magnitude of the residuals, right? And we say this, for example. So let us say that this is def 1. The second definition that we can come up with is, let's take another definition too. Can we use, and reason through this, guys, huh? I'm taking you literally through the discovery process of all of this mathematics of machine learning. It's best to rediscover it yourself so that you understand it. Suppose I did this, epsilon I absolute value, which is equal to the absolute value of.
Residual error.
Now you realize that in situation B, the white hypothesis would do very, very badly. That it would have huge error compared to the yellow line hypothesis, isn't it?
Mhm.
Right? So this looks to be a good candidate for an error. Would you agree, guys? Right? So this is a legitimate. So, well, this looks like a promising candidate. But there is another promising candidate, another way to make this magnitude here, or could be used.
Square.
You square a number this. Will this work? This too will work, isn't it? So we have two promising candidates that will work, right? And now what people do sometimes is, this is it turns out that both of these are valid ways of quantifying error. Are we together? There are names to it. So the first one, when I write it like that, so let me just use the word SSE. Oh, maybe because now we are creating definitions. Let us entertain ourselves with a new color. Which color? Let's try this. I haven't used this, whatever this is. SSE, right? It is also called SSE RSS, right? So let me put these words. SSE stands for sum squared error, right? RSS stands for residuals sum squared. Your textbook tends to prefer this, and this is this, right? And there are people like me who don't like to type so much, so we tend to just write it as E, right? E total, or maybe E total. E is the total error. And this way, sum squared error, let me just write it. All of these things is equal to, all of these are equivalent definitions. Let me just write it this way, is equal to summation of the squares. Are we together? Which is the same as I and yi minus yi hat square. Are we together? This is your definition of sum squared error or residual error. This has been there. Now there is a variant of this that is also used, which is mean squared error, MSE, mean squared error is nothing but your sum squared error divided by the number of points. In other words, the average of the sum squared errors, which is the same as 1 over, I hope this is all very obvious now. Hat square. Is this simple, guys? people use the mean squared error.
So Asif, a quick question, right? So I got the formula, right? But if I'm looking into the model, the one you have slope 0 and the one we have slope equal to some angle. So you said that the one that we have slope 0, the one which is a parallel to the x-axis, is not a good model.
It's
So
not a good model, yes.
on what basis? Because the SSE would be like, if I get the data and if I'm able to plot something like a with a slope equal to 0 parallel to x-axis, then how, like, what is the, how can I quantify that it's not a good model?
Yes. So what will happen is, think about this. If you look at the sum squared, you realize that for the white line, the residuals are huge and the squares will also be huge. So the total error that you will get, so let me just say the error in the error, I'll just use the word E. By here, E, you can use any one of these expressions that you like, a mean squared error, sum squared error, whatever you like. E of the white line will be far greater than E of the yellow line. Would you agree?
Yes.
Right.
But
And you say that the yellow line is a better hypothesis. It's a better model.
so that depends, right? Because in this case, your data is a kind of, if you see the dot that you have, it's going from the positive correlation. But if the correlation is 0, then it's going to be like a more like a parallel to
Yes.
x.
See, very good question, actually. So see, if there is no relationship, if correlation is 0, then you cannot make a linear model, because a linear model would be a mistake. So any line that you draw, any linear line, any line that you draw are all equally wrong. In that case, all of them will be equally wrong. You'll notice that the error from each of these hypotheses that you draw, any line you draw through a data where there's no relationship, all of them will have more or less the same error.
Okay, okay, understood. Thank you.
Yes, good. So folks, this is it. How do you determine that you have learned? Suppose now, okay, so here's the thing. Which is the best hypothesis? Go ahead.
Let's say you have like outliers in the data. How do you guard against it?
Very good question, but hold that thought. So let's learn to crawl before we run. All right, so outliers are a whole topic. Huh? We'll come to that. Now comes an interesting point here. Then the other definition is the mean absolute error, MAE, which is, what is the mean absolute error? It is equal to just what we thought, the other meaningful, right? It is equal to yi minus yi hat, absolute value, right? This. So this is another way to quantify error. So in the literature, you will find many, many things, many definitions. Now there is one more thing. There is something called root mean squared error, RMSE, root mean. What is that? It is nothing but the square root of MSE, right? Which is therefore equal to 1 over n, square root of 1 over n I square, right? So RMSE. So now which one should you use? Like, see, when it comes to the squared family, doesn't matter whether you use sum squared error, mean squared error, or root mean squared error, because minimizing one will effectively be minimizing the other. They are just different variations on the same formula. Do you agree? If you can minimize the sum squared error, you automatically minimize the average as well as the square root. Right? So those are equivalent. So fundamentally, the two kinds of error functions that you learned here, the two variations that you learned is the mean absolute error or the sum absolute error if you want, but mean is quite commonly used, and the mean squared error. Now the question is, which is preferable? Mean squared error, right? Or mean absolute error. Now it turns out that at some different times, different things work. But one of the great works by one of the results of all of this has been the so-called blue theorem, right? Blue stands for best linear unbiased estimator. Quite a mouthful, isn't it? And if you do many fields like econometrics and so forth, you encounter this. So there is a blue theorem, best linear unbiased estimator. And it says that MSE, pick MSE. MSE, or the sum squared error, is actually, people often use the sum squared error. It basically says, sum squared error, MSE. So sum squared error is the one to be preferred. Now, why is that so? There's more to it, to the blue theorem. We won't go into that. Best linear unbiased estimator. Right? We always like unbiased estimators, of course. Now,
as if there's small correction in the MA, it's 1 by n.
Oh yes, thank you for correcting me. That's right. I get sloppy. That is it. Thank you. So now the best, this theorem. So there's a bit of an interesting history, guys. You realize that we have just quantified error. And all that remains now is the second half of the journey. To find the best hypothesis, we have to take that hypothesis which has the least error, isn't it? Like, for example, the white line is significantly inferior now to our yellow line in view of any one of these estimators. Right, go ahead, Albert.
I lost you on that SSE and MSE. So what's the difference between SSE and MSE?
MSE is just the 1 over n average. Just divided that. That's it.
SSE is what then?
Sum squared error. Just add all of them. Don't divide by n.
Oh, okay.
That's it. It's a very
got it.
trivial thing. If you minimize one, you of course minimize the other. So now what happens? There's a very interesting history, folks, to that. And but before I do that, you realize that I'm saying something fundamental. For this, establishing this relationship, this process, by the way, is called regression. Right? Building the best hypothesis to fit to real valued data, X and Y, is regression. A very strange name, regression. Now, regression is a terrible thing in software. Whenever you hear that there has been a regression in the new software build, everybody panics. It means that the software quality has gone down. Regression is the opposite of progression. Right? Regress is the opposite of progress. Now, why in the world would you give this name to one of the most foundational pillars of machine learning? There's a very interesting bit of history. Now, I'll just take a small digression for that, and then I'll give a break, and then we'll move forward with this. See, what happened is that machine learning, these ideas, these foundations of machine learning, how old are they? Can somebody guess? None of my past students can speak up, right? So, because you know the answer. I only want the new ones to guess. Can you guess when this was discovered?
20 years back.
20 years ago, huh? Good. Anybody else? Go ahead.
100 plus years ago.
100 plus years ago. Who's this saying?
Raman.
Raman, and what makes you say who discovered it and how?
I'm just taking a guess. I mean, there were some good mathematicians back then, I guess.
Yeah, that's right. Yeah, go ahead. Turing machine, and yeah, Alan Turing, 1940s, 50s now. Even, yeah. So that is one good guess, actually. Alan Turing, by the way, he created the first real computer. The Turing machine is the computer, the first real computer. And today we call it just computer. And guess what was his dream? It was also to create artificial intelligence and that learning machines. Right, but anyway, when it goes a little bit more back, I'll give you an idea, guys. There was a this goes back to a work, a puzzle actually. There's a bit of history here. And what happened is that in Europe, there was a tradition. The royalties would encourage and patronize the development of science and mathematics, STEM fields, by throwing grand challenges. In data science, that tradition is still there. There's Kaggle competitions and so forth, right? So you would throw a challenge, that some challenge, and different mathematicians and scientists, they would try very hard to win in some measurable way. So there was some challenge, apparently, some sort of a heavenly body. I believe it was some either asteroid or planetoid or something, I forget what, which was in the sky, observed in the sky, but had disappeared. And people knew that it's because of its position, the sun is coming in the way or whatever. You're not seeing it, but you will see it eventually. The question was, where will it show up and when will it show up? Right. Well, that was quite a puzzle. People, it was thrown as a puzzle, and then people tried to all make guesses and submit their guesses. And they were all wildly wrong. But there was one person whose guess was so uncannily on the dot. Some people actually thought there's a bit of witchcraft going on here. Remember those days, people still believed in that sort of nonsense, right? Or something like that. So he made a prediction and he wrote a paper. This person's name, many of you have heard of him, is Gauss. Carl Friedrich Gauss, I believe, is his full name. He's called, rightly so, the Prince of Mathematics. He was a coal miner's son. The coal miner had absolutely believed that it's a complete waste of time not working in the coal mines, but being interested in studies. Somehow he managed to, because of a teacher who patronized him and encouraged him, he managed to thrive in mathematics and do mathematics from a very young age, I believe from the age of 5 or something like that, right? And he grew up to be the leading mathematician of his time, lived to a long age. I am, of course, very fond of him. Machine learning owes a lot to him, the foundational ideas to Carl Friedrich Gauss. So Gauss was the one who solved that problem, and he wrote a paper in 1793. But Gauss was a very interesting character. He used to believe, he had a very interesting definition of genius. So if you ask what is genius, people come up with different definitions. And if you look at the workplace, you notice that people have a tendency that the moment they do a little bit of work, they'll immediately make sure everybody in the company knows, or the bosses know, their peers know that they did this excellent work, right, to get credit and so on and so forth. Gauss had the opposite sort of notion. He said that the best way is that to work really hard, to toil in the night, right, produce a result, and then like a wily fox, go wipe your trails, right? And then when somebody says, okay, this result, and says, oh, this was easy, and walk away. And then let the person figure out it wasn't so easy after all to find that, right? So interesting character. So anyway, he did that paper, but he didn't explicitly say that he used this technique, minimizing of the sum squared errors. In other words, the least squared error. The technique is least squared error, right? So the sum is implicit in that. Least of the sum squared error. The historic word is least of the So another word is hypothesis with the least of the sum squared error is the best. That is what we are trying to say, isn't it? In the discussion so far we have been leading to. So he basically used this technique. Now, there is a story I heard, which I don't know whether it's true or not. I'm told that he was actually in school, and some high school senior, many years senior, student came to him, a friend came to him, and he was doing some chemical reaction equation. And he wanted to help the friend find the answer to something. And in the process of doing that, he had actually discovered it even more many years ago, this concept, right? When he was still a kid. Anyway, He wrote this paper in 1793, that famous paper. Then what happened, and but he didn't explain it very explicitly. Then another mathematician, Legendre, great mathematician, he wrote in 1805, he read the famous paper, least squares, method of least squares, I believe it is called. He was the one who coined the least squares, the method of least squares, which is exactly what it is. He gave it the name. And so the method of least squares has remained. Except that the moment he did that, Gauss rose up and said, no, wait a minute, I should get the credit. I discovered it first, right? In mathematics, this sort of debates, and science is very common. These are called the debate of the prior, right? Who's the prior? Who really invented something, the prior inventor of something? And many people have studied this topic because this is such a profoundly important concept in machine learning. It is the root concept in many ways. So Stigler, a great sociologist and statistician himself, he studied this and he found that actually 3 independent people had discovered it more or less simultaneously. Legendre independently discovered it, Gauss discovered it, and there was a person in US, also, I forget his name, who discovered it. It's in my lab notes. When you read the notebook, you'll see his name. He had discovered it. So this was 1805 when this foundational idea came. So just to know that, you know, much of all these things that you see today, their roots are deep and old, right, of these ideas, of these great ideas. So now I will take a break and we'll go to the next question. All this is fine, but how do we minimize it, right? The second part of the journey still remains. How in the world are we going to minimize this error, right? So that, let's take a break for 10 minutes. Are you guys hungry? Would you like to take a lunch break? I hope not. No, we'll have another 40-minute session and then take a lunch break. So make it quick, guys, 10 minutes break and we'll come back. Let's. To recapitulate, we learned that machine learning needs 2 legs to run on. One is you need to quantify the error. Then once you have quantified the error, the learning process is to systematically reduce the error so that you come to a hypothesis which exhibits the least error. Right? Now, one way of measuring error, one popular way, and it turns out a really good way, is to look at the sum squared error. You can look at the sum squared error or the mean squared error or the root mean squared error. They all are equivalent essentially because they all are the summation. The inner core is the summation of the squares of the residuals errors, right? So that is it. Now, why is this the best? It turns out that when you look at the mean absolute error, and you can come up with, for example, you could ask, why not the 4th power? Right? Why not the absolute value of the 3rd power? Why not many other different ways? So then, as I mentioned, the history of it is very interesting. 1805 is the Legendre paper. 1793 is when Gauss thinks he did it before, and he was right. He did do it. In, I believe, 1812, there was a landmark result that Gauss published. It's called the Gauss-Markov theorem. So the theorem is Gauss-Markov. So which says, and I think I said it when I said blue theorem. Blue theorem is the result, not the theorem is actually Gauss. I just remembered that I sloppily said that Gauss-Markov theorem. It said that the least squared error is the blue. When you square the errors and you look, whichever formula you take, it gives you the best linear unbiased estimator. Quite a mouthful, and we won't go into the proof or the too much details of it, but basically consider it that it is a good idea to take that. And I'll give you sort of an intuition. I don't know if this intuition is mathematically rigorous. Most likely it is not, but I'll sort of give you. See, one of the rules of parenting is when your kid makes small mischief or mistakes, you deliberately look the other way around, right? Try not to notice it. Bad parenting is to micro correct the kid for every mistake. We all know that as we parent it out, you deliberately make sure you don't look at the small mistakes. You let it happen. You treat it with a form of benign negligence. But if the child makes any mistake that's dangerous, that can hurt the child, right? Or that can form a really bad habit that will hurt the child later on, then you step in, right? And have one of the talks.
Outlier.
Outlier, exactly. Stronger, yeah, exactly. Bigger residuals. So what you do is you have amplified response for big errors, but small errors, you just let it be. I often think that that is a good intuition, because when you're building a model and you're learning, think of your hypothesis of the line. It's a learning process as a child. What you want it to do is the small errors you sort of want to ignore, and you want to amplify and make the big errors the teachable moments, isn't it? So when you square the errors, big becomes bigger, right? And small remains small relatively. So the square of 2 is 4, but the square of 10 is 100. You see the difference, right? So the bigger ones get amplified. And so when you take the sum squared error, you're much more sensitive to what may be real deviations, real residuals. Small residuals can often be because of something, but because of noise in the data. Every data that you gather has instrumentation error or some form of error, and we'll talk about it. The next concept we'll talk is irreducible error in a moment. The word, make sure that today I do cover irreducible error. So you want to not be learning from noise. That would be foolish. You want to be learning from the real signal, which is the actual residuals, significant residuals. Go ahead.
So if you want to make the application more specific, would you then use powers?
Would you then use?
Like this is power neural
Powers? Yeah, so that is it. The trouble with that is using very high power. So now from 2 is good. Why not power of 10? Right? The power of 10, what it will do is only the outliers will speak, and they will completely hijack your model. Right? So you don't want that either.
In the past, I've also seen one more error measurement of MAPE, M-A-P-E, right? The mean absolute percentage error. You didn't mention that. Is there a reason?
No. Yeah, so there are many such things. I'm just mentioning the big ones, right? But you can have all of that, right? So it is mean absolute error. From there, you can go to mean absolute percentage error, right? They're
It
equivalent.
normalizes in a certain fashion.
That is it. That is all it is, right? But the big idea is these are what is called the norm, first norm or the second norm, like typically you look at that. Right? And we'll talk about the norms a little bit later, Minkowski norms. So there is that. So, this is the trade-off, and that's why there's a Gauss-Markov theorem that says, hey, too much of a good thing can be bad, right? Don't go about taking the 10th power of it or something like that. Then only the outliers will speak, and they'll dominate the learning process. Right? You don't want that either. And it so turns out that the square is the best you can do. In fact, most people don't even know that mean absolute error also works, actually. I suppose a lot of people know, a lot of people also don't know. They just know that the only way to do compute errors is sum squared errors. Right? For a reason, it's become ubiquitous in most of the programming libraries. So now,
Quick question. So usually is there a range that this SSE will lie, or it can be anything?
I didn't follow. Is there a
Range.
So
range?
minimum.
No, there isn't. There isn't. This is a good question, actually. We'll see in the data as we go to real life data, not today, but in the next lab. See, what happens is that you try to see to ask the question, what value of whatever error you pick is good value. The number, it is not in absolutes. It is from the data. The way you say that is given a data, it doesn't matter the size of the error. What matters is the relative size of the errors. That hypothesis, which beats other hypotheses in having the least error, is the hypothesis you want to go with, right? So let me explain, let me say this by a landmark statement in machine learning or in data science. See, guys, data is manufactured by some causative force. When you see data, You don't know the causative force, right? People have not given you the equation, because if they gave you the equation, the whole point of data science goes away, right? It's already done. Your whole point is to discover those or hypothesize what those causative equations could be, right? Now, here's the thing. You can come up with many equations or many models or many hypotheses that fit the data. So long as they make reasonably good predictions and have small sum squared error, they are all good models. You just are picking from the best, right? So there is a statement in machine learning, in data science. It goes to the great data scientist or statistician named Box, right? Box, literally B-O-X. He said famously that all models are wrong. You will never know, even if your model makes perfectly good predictions, whether it is exactly that or there's some other correction to the equation. This is a broader statement. In science, no theory is right. You can only prove it wrong. You know, remember the falsifiability of theories. You can falsify them, but you can't prove them to be true, right? So Box says all models are wrong, but some are useful, right? So the pursuit of a data scientist is to find useful, effective models, effective hypotheses, not the correct hypothesis. In fact, whenever you say, somebody say, oh, my model is correct, it is a sign of ignorance. Not only have they not understood what they're doing, they haven't actually understood the whole point of data science and science itself. Science is not about correct. Correct is a constructive definition. You say, if it agrees with data, aligns with data, it is in quotes correct. And it's simple, it's correct, right? Generally, you say that anything that aligns with data and also agrees with the Occam's razor principle, namely, of all the models is the simplest one, right? The simplest explanation. The Occam's razor principle says that the definition of correct in science is the simplest, effective explanation is considered or defined as the correct explanation. Are we together? So for example, let's take Newtonian gravity. You say force is a gravitational force is proportional to m1, m2 over r squared. I hope all of you are familiar with it. Well, you know, you could write all sorts of complicated equations. But this is amongst the simplest equations that perfectly agrees with the data, at least unless you do very fine, like long range corrections in which Einstein's gravitational equation needs to kick in, right? Einstein's equation in the large, right? G mu nu is proportional to R mu nu, which basically says the energy at a given point in space-time is proportional to the, actually to the curvature at that point, which is again proportional to the mass sitting there. Right. So very simple explanation. It basically says that a heavy object just changes. If you think of space-time as a fabric, you put a big object and the thing develops a dip, right? You take a stretched out fabric and you put a big object, it will develop a dip. And the amount of curvature the dip it will develop will be proportional to the mass. And that's all that Einstein's general theory of relativity says. Utter simplicity. Right? Of all the complicated explanations you can come up with for gravitation and so on and so forth, this is by far the most elegant and simple understanding of gravitation, right? And so simplest explanation is the correct one. So just keep that as a background. We are going off on a tangent, but the basic point is that you look for effective, simple models. That is your purpose. And simplicity is the Occam's principle. It has to be right. It has to be working. It must work. I mean, a simple explanation can be wrong. That is not the definition of correct. You define correct as the simplest effective model, right? Or hypothesis as the correct answer. Right? It's a constructive definition. Come again?
You define or you choose?
No, you define. Occam's razor principle says that in science we define correct to be that effectively. So it says that the simplest explanation is the correct one. Right, but implicit to that simplest explanation should actually work. It should be effective, and is the correct one means it effectively defines what is correct. Right, it stays that. That's the Occam's razor principle. Right. So anyway, we'll leave that. Now comes the interesting thing. Can any one of these error measures? So I'll just focus on the least square error, sum square error, and so forth. Can the error be zero? Can we minimize it to zero? And so for that, I will ask you to look back at this data. Do you notice that they are residuals? Can you ever make a line that goes through every point? No, right? Right. So what happens is that there are two aspects to the errors that you are left with finally, after you have done fitting the best model. One is called a reducible error. One part is called the irreducible error that remaining error. So once you've done the best fit, then there are errors that remain. So one could be the reducible error is your hypothesis itself is barking up the wrong tree, right? So for example, if the real relationship is like this, and we will do this in the lab today afternoon to illustrate this point, suppose the real relationship was like this. Data points like this. Right. In this data point, suppose you make a straight line hypothesis. You say, I'm going to fit a straight line to this data, a linear regression. What will happen is perhaps your best fit straight line is this hypothesis A, right? A linear hypothesis. There can be a hypothesis B, which may be B. Which of the two hypotheses will give you less error? B, right? Now what happens is the first one says fit the best line. The second one says fit the best two-bend curve to the data, right? And the least square method will help you find either the best fit line or the best, this pink line, pink curve, right? So the HA suffers from more reducible error compared to HB because you have chosen a hypothesis which machine learning will just fit the best line, but it is not a line, isn't it? So these sort of errors are reducible errors. And this goes to the heart of things like bias and variance, but I'll give you a taste of it. What it means is that your hypothesis, or yellow line hypothesis, is simpler than the ground truth, isn't it? It is simpler, it is simplistic, relatively oversimplifies the ground truth. When you oversimplify the ground truth, you suffer from a kind of error which are called bias errors, right? The B, the pink line hypothesis, pink curve hypothesis, is in this case, it's appropriate. It seems to be aligned with the ground truth, more or less, isn't it? But let's take yet another hypothesis, which goes like this. What about this? It's a far more complicated curve, right? You say this hypothesis, would you agree that it is more complex than the underlying ground truth? Right? It is too flexible, too complicated. Generally, when you take a hypothesis which is which sees more in the data than you should see, basically, right? Which sees that, then you have what are called variance errors, right? So see, when you have data, you don't know a priori which of the hypothesis will work. It is your job to fit the best yellow line, the best pink line, the best green line. The least square error will help you just make the best fit within its class, the straight line class, the pink class, or the green class. But you have to know which of the three hypotheses you should have started out with is something you have to do by trial and error. So that is often called a hyperparameter of the model, right? In other words, you can't learn it. You have to try and do it and see which is the best hypothesis. right? And so those errors which come because you didn't choose the right hypothesis, you can have a better hypothesis. These are your reducible errors, right? Or for example, you take a line, you fit a line that is like this. You haven't done your learning. You didn't run your learning algorithm long enough, and your line still says like this. You realize that there is a journey from this line to the HC to HA. There is still an error that you can reduce by running your learning process longer. These are all generally the ideas of your reducible error. Now, what are irreducible error? Do you notice that even if you take the pink line doesn't exactly predict all the points, or there are still residual errors. These errors you can't get rid of. These are irreducible errors. Why do these errors occur? Think back at your ice cream situation. Let's say simpler situation of the ice cream and the entrepreneur. Could you explain, if you say the sale of ice cream only depends on temperature, you have a best fit line and you have irreducible error. What is the cause of that irreducible error? Can you make some guesses?
I think it depends on some more variable.
Yes, it could be based on flavors. Somebody has more flavors, sells more ice creams.
That is right. That is right. Whether you chose the right flavors that you brought in that day, right? Other thing is it a work day or a weekend? Is it a holiday? Weekend or holiday, right? Because given the same temperature on a weekend, you'll sell far more ice cream because parents are free. They'll bring more kids there than on a work day, right? So that which the model doesn't know or cannot learn from, the data that is missing, the important features or predictors that are missing, they cause the irreducible error. So what if you ask this question? What value of sum squared error or the error, whichever error you take, tells you it is good? There's no clear answer, but the only answer is when your sum squared error is pretty high, or mean squared error, whatever, error is pretty high, it generally means when your irreducible error is pretty high, your minimum irreducible error is still pretty high, it is an indicator that there is a lot that you missed. Right? There's a lot that is unknown about this. It happens, for example, in sales. Whenever you try to sell and you advertise and do things, generally those people, they build models in which the sum squared error remains very high. So there is one way to quantify learning, and which we will come to right now. It is called the coefficient of determination. Let me get to that. We will now learn about a concept. Quite a mouthful, isn't it? This is often written mathematically as R squared, capital R squared. And people often, most people colloquially call it the R squared. It is one of the most popular measures of learning, how much your model has learned. So how do we do that? What you do is you compare it to no learning, right? So let me explain what it means. This. Consider back the same data. Oh, what just happened? All right. Consider the same data. Or should I measure it in pink, blue? Because the last I did it in blue. It is the same data. See, this is your X, Y. Now, you can build all sorts of hypotheses. One hypothesis is called the null hypothesis. The null hypothesis. This is a special hypothesis. See, on this page, you can draw any line that you draw is a hypothesis, right? So, for example, this line, right? This line, right? this line, this line, this line. How many lines can I draw on this? Infinitely many lines. Each line is a hypothesis about the relationship between X and Y, about the amount of ice cream that you will sell and how it depends upon temperature. One hypothesis says the more the temperature, the less ice cream you'll sell, right? Another says, no, it's more, and to what degrees, and so on and so forth. There are different hypotheses. Of all of these hypotheses, one hypothesis is special. This hypothesis says this is the null hypothesis. It says that there is no relationship whatsoever between how much ice cream you'll sell and the temperature. Are we together?
Mhm.
That there's no relationship whatsoever, right? Now, if null hypothesis says effectively that it's pointless for you to try and find a relationship. There is none, right? That is why it's called the null hypothesis. So the null hypothesis would say, just take the average value of y. Y hat will always be y mean. Take the average value of all the observed y's, and irrespective of x, it will always be that, right? That is your best estimate. So now this is your base error, total sum squared error, whatever error you get for this. Actually, the book uses this term. If you forgive me, I will use the term as E phi, the error of the residual errors of the sum squared residual error, whatever means you want to take, sum squared error of the null hypothesis. Are we together? Sum squared error. Actually, your book uses the word RSS, so we'll use RSS. Sum squared errors of the null hypothesis, right? Now, let us say that you take another line, you come up with a hypothesis, a different hypothesis. Let's say that you come up with a hypothesis like this. Let me just call it H. What should I call it? 1. And let's take another line. Well, I foolishly used pink for the axes, which I shouldn't have, but let me use something else. Let us take another line, which is green. Let us say that I have a hypothesis like this, H2. And I can have an hypothesis, which is, which color should I take, which will stand out? Let me take yellow, I took green, I took blue. I'll just use blue, or let me take this. Let's see about H3. Just looking at this picture, you would probably agree that the error of H3 will be even worse than the null hypothesis, isn't it? So this is actually an important point. Most people don't realize that you could do a learning exercise and what you have learned is actually terrible, right? Yeah, you actually can learn worse than the null hypothesis. Yeah. Which is, this error is greater than, I suppose, H of H2, the green line. Would you agree with this? Right. Actually, let me color the lines with the error words appropriately by their color, line colors. Would you agree that this is true and this is greater than E green of the green line, which is H2, and that is greater than E error of the small one. Would you agree essentially to this inequality just by doing a visual inspection of the data of the plot here? Isn't it? Now comes the question, how do we quantify that one is better? I mean, instead of looking at the total error, what people have come out with is, they said this, if you take the error of a hypothesis, of any hypothesis, right? Here, let me use white because I don't want to use pink here. E of a hypothesis, error of a hypothesis or a model is equal to the sum squared error. I mean, sorry, not this, there's a word for it. It's called R squared. For historic reasons, R squared. Take the error of the hypothesis, subtract the error, the initial error of the total of the null hypothesis. You know that this is hopefully positive number. Isn't it? Would you agree that hopefully positive? Negative. And then you ask yourself, relative to the initial error, because you know this will be a number, but let's scale it down and say proportionately how much did you learn? Right? The initial error, the null hypothesis error, right? Would you agree that this would be a pretty good measure of learning? So let us unpack this and see if there is no learning. If EH equal to E phi, approximately equal to, like very little learning. Very little learning, R squared would be, numerator would be, if the error of the hypothesis is very close to the error of the null hypothesis, what would be the numerator?
0.
And so 0 over whatever total it is, this will be close to 0. If on the other hand, let us say that there is perfect learning, right? If EH is close to 0, let's say that there's very little irreducible error remaining, what will happen?
1
Then R squared
is 1.
equal to 1. It will be a little less than 1 because there'll always be irreducible error. It will be. So means good models, good hypotheses will have a high R squared, and not so good hypothesis will have.
Close to 0.
Is there something cooking? 1 second. This is the coffee pot that was filling this space. Okay, so what do we conclude from that? R squared is a way to quantify the amount of learning. Quantify the fit, the goodness of fit. People use this word, goodness of fit, of a model to data. Are we together? This is it. It takes value. So R squared is always less than 1, less than equal to 1. Can it be 0? Some people think it is between 0 and 1, which is generally true. But if you look at the blue hypothesis, what do you realize? R squared can be negative, right? So it has picked up some junk, right? It has learned some junk. It does happen, actually. It does happen. So this is it. This is the meaning of R squared. It is the coefficient of determination. Come again?
Why is it called square?
Yeah, see, the word R squared is historical, right? I wouldn't put anything to it. The right word is coefficient of determination, but people don't use that word. Most of the Python and R libraries, they keep using the word R squared. Yeah. It's a fact. But obviously the point remains that, you don't call something a square if it can take negative values, right? It's historical, right?
So I have another question. For the null hypothesis, you said that you take the y to be the mean, right?
Yeah,
So which means that it depends on the distribution of what you took as a sample. You
exactly.
did that.
Yeah.
But if I put some other function which kind of says, hey, I need to give a little bit more priority to the guys on the right, that value of the y would have been further up.
Yeah.
Now you're like changing the whole dynamic. So how do you?
So you're
put
basically
that
saying
into the-
this yellow line, I could
Yeah.
lift up and down.
Correct.
Right?
Right.
So yeah, see, you have to, as a convention, pick one of them as the null hypothesis. So by definition or by convention, people have said that the null hypothesis is first, y has no relationship to x, it's flat.
Okay.
The second is, now which value of y?
Yeah.
Just take the mean of observed y's.
No, but do you like take a sample, say, suppose you have 1,000 points, right?
Yeah.
You take like, say, 200 like that randomly and then
Yeah.
do the mean and do it, or
No, you
you
just,
don't need to.
yeah,
The
typically
1,000
do.
is typical of if you went and did subset.
So typically what happens is that when you are learning the data, you have the data.
Huh.
You don't know whether it's the full data or it's the sample.
That was
But
what-
whatever it is, you say, for that data, the null hypothesis is whatever is the mean.
Okay.
Yeah, that's how you do it. And then you always hope that if you never build a model once, you build the model many times over. All right. So then the center limit theorem will kick in because the mean of the means will be stable.
Yes, yes.
So that is it, guys. So now we have a way to measure, at least one way to measure the goodness of it. But the fundamental question still remains, how in the world do we minimize this error? Right? So there are two ways of doing it. So two good ways. So one is, of course, a silly way. One is, so I'll exemplify it with a simple thing. You do this thing in normal software engineering. You do sorting, right? Is the bane of all undergraduate classes. The moment you enter undergraduate algorithm, the first thing you do is sorting. There's bubble sort, there's radix sort, there's merge sort, there's a quick sort, and God knows how many ways of doing sorting. I mean, it's a whole world of research, sorting, efficient sorting. Right? So the pursuit is always for the best sorting algorithm. But there is actually a worse sorting algorithm too, right? So what do you do? Suppose you have to sort some items, comparable items, numbers, let's say. What you do is you just shuffle them. And then you check, is it sorted? No. Oh, shucks. Let me shuffle it again. And then you see, is it sorted? Oh, no. Oh, God. Okay, let's shuffle it again. And you can keep doing it so that one day you'll end up with a shuffle in which it's truly sorted. It's a valid algorithm because one day it will converge. It will terminate. But surely you don't want to try that.
That's like buying the lottery ticket. Shakespeare.
What's that? Is monkeys writing Shakespeare? Yeah, typing out Shakespeare. All right.
Buying the lottery ticket.
Or buying the lottery ticket, yes. So so in the same way, one way of finding the best hypothesis is to just keep on drawing lines. What does it mean? Is each line is uniquely defined by a slope and intercept, beta naught, beta 1, isn't it? Just take random values of beta naught, beta 1. Take 10,000 random values. And for each value, right? For each value, compute the R squared and find out that one which has the lowest R squared or the lowest sum squared. All of these are equivalent. Are we together? And then you say, I got that one. Totally silly as they sound. Actually, many times when I see software engineers do work, because we live in the world of big data and distributed computing, you often find them finding brute force solutions like this. Take lots and lots of experiments because you have so much computing power and pick the best. It's sort of like our sorting. Now, there's a problem with that. First is it's computationally intensive, may take forever, a long time, and you never know whether any one of those solutions are really close to the optimal solution, isn't it? It is really close to that H1, the lines that you pick, because there are infinitely many lines. Even if you picked 1,000 lines, they may have all been far from the right answer. So picking the best amongst them is still no guarantee that it is an effective model. So there is a way actually to systematically find that. And that brings us to the other profound concept, which is that of gradient descent. We'll learn that. It's a very important concept. We are going to learn that today. And that would be the last theory topic for the day. Right? Then we'll all take our hungry stomachs to lunch. So gradient descent, what is that? The topic now is gradient descent. So gradient descent is something very simple. First, we will try to go back and look at some basic mathematics that you may have forgotten, but I'm sure coming from STEM fields, you have all done at some point. Do you realize what when we write y is equal to function of x, some function of x, right? We plot it out as this. Given x, we can have a curve. Let us say the curve is, just by choice, let's say that the curve is like this. This sort of curve are interesting curves. See, I could have drawn all sorts of wiggly curves like this or whatever it is. I didn't. What is different between this curve and the curve, the big curve that I drew? Simple. It has one bend. Do you notice that? It has only one bend. The word that people use is that it's a convex function, right? Bulge. These are different, and then we'll go to that. But more importantly, these are convex functions, but it need not be convex. In the world of machine learning, it turns out that non-convex functions, etc. But the point is, it has a minima. This point is called the point where y achieves a minimum value, right? So this particular value, what should I call this value? Star, x star, right? X star is where this is y star, this particular value of y, right? And this particular value of x. Let me just remove it here. X is here, x-axis is here. This particular value of x and y represents a unique point as the bottom of the valley, isn't it? Bottom of the curve. X star, y star. This is called a minima, right? So you say that x star is the argument of which x value will minimize y. Which value of x will minimize y? It's a minimum. It's a fancy, actually forget argument. Let's not use all of this. Minima, it's a minimum point, right? Now, how do you find this minimum point? Let's do that. Suppose that you are here. Suppose I take this point here, this arbitrary point to the left. Let me call this point A, right? Now observe, we will look at the slope here. If I move unit distance, positive delta x, does y increase at this point or decrease?
Please.
At A, delta x leads to y decreasing, positive. Can you please mute yourself, guys? What about B? Suppose I take another point, let's say B. So actually, let me put B here and A also here. So A and B are points in the XA. So let me just actually, I could use, let's agree on some convention. XA, and this is XB, We'll call this point A and B. All right. Now, what about this? What about B? At B, at A, delta X, if you move one step forward, delta X leads to Y increasing. Right? So what you say is that at B, the curve is rising. It has a positive slope. Right? That's literally what it means. Slope is defined as delta Y over delta X. How much of Y increased over for every unit increase of X. Clearly at B, you would say the slope delta Y delta X at B is greater than 0, isn't it? And delta Y delta X at A is less than 0. Would you agree with this, guys? This is visually obvious, isn't it? Right. Now, suppose, well, you could say that if you want to find this place, this is the point you want to find, right? Go to somehow, all right? So let's call this home. You want to find this point, the optimal point, it's your home. And you're a little ant, right? Imagine yourself a little ant on this curve and you want to go home. But you have the ability to tell what the slope is. Which way are you going to fall, right? If you don't grab onto the slope. Can you find your way home? It's very easy. At X, what do? You take a step in the direction of the slope or against it. Look at A, slope here is negative, means if you take a step forward, Y will decrease. Do you want that to happen? Yes, because so at A, you want to keep making steps forward, right? What about B? At that, slope is positive, but you want to make steps like this, against the direction of X axis, opposite to that. So we can say this statement that those little steps that you take, let me put it here, the next at B, at A, your next value of X should be, X next should be XA minus, you take a tiny step, but in which direction? Because slope is negative, negative of a negative is positive. So suppose I do this, a plus minus slope. Would that work? Because my X would become X next. This would be positive, right? Because minus would go against the slope, minus of the slope, and it will become a positive quantity. But then how big a slope, how big a step you take, you can control. You may say, let me take a tiny step in the direction of the slope, right? Against the direction of the slope. Are we together? So then you would be going in the right direction at A. Does that make sense, guys? Isn't it? Slope is negative. So suppose I go minus of the slope and a tiny bit of it, means I took a tiny step in the right direction, right? At A, at B, what happens? X next should be XB. Now look at it, slope here is positive, but you want to go this way, you want to go back. So is this the right way to go back? Right? And let's make a smaller step, not make a big step, just in case the slope is huge. Would this take us backwards? Okay. So in both of these situations, it would take us to the correct place. And what about this place when we have reached home? What is the slope here? 0. So we won't be making any steps anymore, isn't it? Go ahead.
Why can't we start at the point where X1 and X2 is 0?
Because you don't know where it is. See, in a function like this, you could say, hey, you know what? Let me take the slope and set it to 0. the problem that happens with this is, in this picture, it's true, but suppose you grab, I mean, there's a whole complication. This real simple curve doesn't actually happen in machine learning often, right? What happens is that you get a world in which you get a reality, first of all, multidimensional reality, and then you get a curve like, right? So many places. You see that, right? So those are the issues that come with this. Go ahead.
Why are we just taking one step? Can't we progressively change like the amount of step we take based on how close we are to the zero value?
That is right. So that brings up, so this alpha, the size of the step. See, what happens is, okay, so I'm coming to that. Hold that thought in your mind. I'll gradually build into it. So let's generalize from this fact. Do you notice that whether you're on the left side of the answer or the right side of the minima, the equation looks exactly the same, isn't it? And this is the celebrated equation called the gradient descent equation. It says that the x next value of something should be x minus alpha and the alpha times the slope, right? dy dx. Now we can generalize this to higher dimensions. Okay, so before we do that, this is the gradient descent. Equation. Now, this is called the learning rate. How big a step are you willing to take? Typically, you take tiny steps, 0.01 times the slope and so forth. Why? Because let's say that you're here and you take a big slope, like suppose you're here, where should we say? You're here and you take too big a slope, you might end up rising, getting to the wrong place, right? So you don't want to do that. So learning rate, and we will come to the learning rate in the, when you come to the deep learning workshop. It's a very important concept. You worry about the learning rate and should the learning rate keep changing at different stages of the learning process, right? Quite a bit, there's a vast literature there, right? But at this moment, we'll take it to be a constant. And just pull it out of your hat, pick a number, small number, just keep it small, right? Don't take it too small because then you'll just be sitting in front of the computer and waiting for it. So in our profession, actually, data science, there's a very easy way to goof off in the office. You're playing ping pong. Your manager comes and says, "What are you doing?" Says, "Oh, my algorithm is learning." Right? I'm babysitting it. Right? So no, one easy way to do that is to take very low learning rate. It will take forever, right? Not that. So be judicious about it. And now let's take a generalization of this to higher dimension. What is dy dx in higher dimension multivariate calculus? You know, when a y is a function of x1, x2, x3, x4, the general is the same thing. It's generalized to the symbol dy dx generalizes to, like, what you may call effectively the x vector in some sense, right? Because now it is x1, x2, x3, x4, but this is equal, it is called right? It is this symbol. This symbol is the Nabla symbol, right? Or people just call it the grad of y or the gradient of y. Are we together? No change. There's nothing magical here. We just generalize it to higher dimension, right? This is it. And so this equation therefore becomes the x next would be, if it was not a curve, but a surface, right? A two-dimensional surface or three-dimensional surface or so forth, this would be x minus alpha, the gradient of y, right? And x would of course now be a vector, right? This is what it would be, right? This is your famous gradient descent equation. What it basically say is that, and it's common experience, those of you who go hiking, what is the path of steepest descent? What is the fastest path to the bottom? You don't want to take that. Right? Right? But it should, right? But you all know intuitively what is the fastest path. Go down the steepest path.
But you learn fast also.
You learn fast also, right? So every time you slip and fall in the hills, you are taking the path of steepest descent, right? But while you don't want to do that to yourself, when you're in the world of machine learning, you want to get to the answer as quickly as possible. So you do take the path of steepest descent. This is also called the path of descent, right? So this is it. Now comes the thing. How is this basic theory applicable to our loss function? We are going to come to that now. Now, what is the time? It's 1:24. How many of you would like to take a break at this moment? You guys would like to take a break at this moment. Okay, guys, let's do that. Let's take a break for lunch. Right? After that, I will relate it now to our error function and put the two together. And so you will learn, you will actually know what the learning, how the efficient learning happens in machine learning. Right? So let's pause the recording, Kyle, at this stage. So guys, look at this ball, right? What was a curve in 2 dimension? What does it become? It becomes the shape of a ball, right? This curve that I've been showing, if you look at the screen, this curve, and look at this ball. In 2 dimensions, this is your surface, the function surface. So if you're inside the ball, imagine that you're inside the ball. What is the path, the shortest path to the valley, to the bottom? You want to literally tumble down the path of steepest slope, isn't it? That is your path of steepest descent. Fastest path to the bottom is, if you're a little ant, and the fastest thing is you just go like this and you'll tumble down straight the steepest path. Do we agree with that? That is why it's called the steep. As opposed to most of you, when you are hiking, what would you do? Let's say that when we are hiking, it's more like this. You're at the top, you want to come to the bottom. You will gradually circle around and around and around and around. Is that the steepest path? No, it is just gentle gradient to the bottom. If you're inside also, you'll do that. Imagine that this is the Yosemite Valley and these are the hills around Yosemite. What will you do when you're hiking? You'll slowly make your way down, isn't it? And that is the difference, right? That is what we are talking about, this gradient descent or the path of steepest descent. The reason we learn like this is because it's the most efficient way of learning, as opposed to randomly drawing lines and doing it. So now, what does this mean with respect to this graph here? What happens is, this thing, right? This is a surface. You could have taken a path inside, like gradually coming to this, but the steepest descent path basically says you are down to the bottom, right? The steepest part. You make little hops from here to here, to here, to here, to here, and to this part. Now, one interesting thing that comes up, you don't want to make too big a steps, because in the extreme case, if your steps are too big, let's say that you are making this big a step, A is very big. What will happen? You will overshoot the minima, isn't it? You instead of reaching home, you'll go way past it. And then you'll again want to make a jump, and then you'll keep jumping. So you'll keep oscillating around the minima, right? So that is why learning rate is important. Small steps are better, but too small a step means learning is very slow, right? So this is it. Now the whole question is, this is the great, let us now relate it to our problem. Our problem is this, once again, and now I will teach you about 2 different worlds, an abstract world, a space of hypotheses, and the real space of data. What is the real space? XY coordinates. It contains your data, isn't it? So let us, and this is a very crucial point that I want you to see. So two worlds. Two worlds. Data space, and I'll use the word space because that's what people use, but if it helps you, think of two different worlds. Data space, it is made up of X, Y, right? In the XY world, data manifests itself. The data that you get from which you have to learn is here. Right, let me throw some more data here, forgive me for my bad art, but we'll go with this. Are we together? These are actual observables. Right? Now, any hypothesis that you make, let us say you make a hypothesis. I'll just make a random hypothesis. Let's say that you make a hypothesis H1. This hypothesis is a line. It is, at this moment, we're only talking about lines here. This is uniquely specified, or in common sense is defined by slope and intercept. If I give you the slope and intercept, there is but one line that you can draw, isn't it? So the line is same, therefore H1 is the same as beta naught, beta 1, intercept and slope. If a unique value of beta naught, beta 1, isn't it? That is it. So now what we do is we think of another space here. You would agree that this thing belongs to some point. In this case, slope is negative and intercept is positive. So it is probably a point here. Let me use the word A. So this is beta naught, beta 1 for point A. Isn't it? This is beta naught axis, and beta 1 axis, slope axis. In this imaginary world, the hypothesis space, would you agree that this is it? No. You can see that the A line corresponds to a point in the hypothesis space, a particular value of beta naught and beta 1. This is simple, isn't it? Likewise, if I make another hypothesis, let us say I make a hypothesis like this, HB, this gives you negative slope, a negative intercept, let us say, and a positive slope, negative intercept and a positive slope. Let me call it B. So beta naught, beta 1 to the point B. Would you agree that here, this is your point B in the hypothesis space, right? If I take another hypothesis, which is like this, HC, positive this and positive that, C. In the hypothesis space, it is this point. And then perchance you end up hitting it quite close to the right one. Let us say HD. HD may be somewhere here, right? D. More intercept than C, but the lesser slope. So this is it. You're positioning each of your hypotheses in the hypothesis point. So in other words, there is another world of hypothesis space. And what are you doing? In your hypothesis space, you are saying, how can I, suppose I start with a random line. Suppose I start with A. The question that we have to ask is, what is the most efficient path from this to this, from this to this, from this to this, from all of the different hypotheses to D, isn't it? How do we go from this not so good lines to the best line? Right? So I can pick some random values for the hypothesis. Initial hypothesis can be bad. It will make a huge error. Now, how do I improve my hypothesis systematically so that I can reach the hypothesis D as quickly as possible, right? In other words, how do I find, if at all possible, a quick and shortest path from here to here, from here to here, and from here to here? That is our problem, isn't it? That is what we would want to do. So now observe that at each point in the hypothesis, there is also the error associated with hypothesis A, error associated with hypothesis B, error associated with hypothesis C, D, and error associated with hypothesis B, isn't it? At each point in the hypothesis space, we can compute the sum squared error because it is that hypothesis will produce, with respect to the data, a certain error in prediction. So far, so good, guys. Are we understanding this? And so we can now look at this data in a more three-dimensional way. Let's look at it. What we are saying is something interesting. Let's say that this is the beta naught axis, this is the beta 1 axis, and this is the error associated with a given beta naught, beta 1, right? So now look at the error. Your error is, let's say that we are looking at the sum squared is equal to summation of yi minus yi hat squared over n. So this is your error. I'm just taking the sum, forget 1 over n and all of that, right? They're all equivalent. Now, what was our hypothesis? Our hypothesis is yi minus beta naught minus beta 1 xi. All I do is substitute the fact that this is equal to beta naught plus beta 1 xi, isn't it? The prediction is the value by plugging in the lines formula. You agree with this, right? So far, so good. This is a very crucial point. Please make sure you understand that. Oh, forget that. Forget divide by n. Who cares? I mean, ultimately, it's the same thing. If you want to, you can divide by n, right? Oh, of course, I forgot the square, right? So now, when you are learning, when you are moving from one line to the other, think about it. Is the data changing? No, no. Data is a given. You're learning from the data. So in this equation, data is fixed. So this E is actually as you change the value of beta naught, beta 1. In other words, you change your hypothesis. The error value for the hypothesis keeps changing, isn't it? So E is actually a function of beta naught, beta 1, isn't it? And it is equal to this, or also written as E as a function of the hypothesis, a point in the hypothesis space, right? Error. And that is it. E is here. So what it means is that in this plane, if you take any one point, there would be a certain error, right? Let's say that this is D. And what will happen is, now let's look at this equation. Does it look in beta naught and beta 1? Does it look like a quadratic equation? It's quadratic, right? If you expand the terms, will it be quadratic in beta naught and beta 1? That's true. And when you take the sum of squares, can it ever be negative? No, right? So however much you minimize it, it will still be a positive value. And what does a quadratic curve look like? You would agree that a quadratic curve looks like this. The only question is it pointing up, pointing down? We know that it has to be pointing up because it has to be lifted off the ground. You know, there is a residual error irreducible error that will remain, right? So now generalized to beta naught, beta 1, this is a surface, right? So let's draw the surface out. What will happen is it is looking at well, okay, I did not center it. I'm terribly with this plotting. So let me take another color. It is actually what is a parabola becomes a paraboloid kind of thing, right? Isn't it?
Good thing that India has the glass,
What's that?
the one below the glass thing that you have. See the glass was.
The was, right.
Yes.
Right, exactly. It's sort of that, right? So, or it is like this too, the same thing,
Yes, that's right.
the error surface, right? So that's why you need to keep this when you're learning machine learning, right? So now this thing has a minima and you realize that D is the minima, but now you can look at the contour lines. If I project the values, the points of this down, you would agree that they form contour lines. These are called contour lines. You know, what are contours? Points of equal value of the error on the surface. They, when projected down, form this circle. Right? Ellipsoid, rather, not circle. These ellipses, they form in the beta naught, beta 1 plane. And so what happens is that, suppose you are here. What does this correspond to? Let's say that here. Suppose you happen to be this hypothesis, for the sake of argument, pick a number. Let's say A, right? You are here. This is your hypothesis A. This is the error for hypothesis A. This point is the error for hypothesis A, the height of this, right? What do you need to do? You just need to use the gradient descent to keep doing this, reach here, right? So you need to find a path to do this. And the fastest path is gradient descent. So basically you do the gradient descent in the hypothesis space. This is very important. In the beta naught, beta 1 space. Are we together? And this is how your error surface looks. And this is the iconic diagram in this field, guys. Try to remember this, right? That you are doing gradient descent in the hypothesis space. People often use the word, say, I use the word hypothesis space, but I'm probably sort of not very commonly people use it. It is called the parameter space. That is the common term that we have. What are the parameters? Beta naught, beta 1, because those are the parameters of the hypothesis, isn't it?
So the circular thing
Yeah.
below is the
Projections. These are the projections of the contour lines. Right?
so
So
that is called the parameter space. That's what it's-
yeah, this is the beta naught, beta 1 is the parameter space, right? And if you can include the error also, the 3-dimensional space is your parameter space. I just call it, so parameter because hypothesis is uniquely defined by its parameters, right? Yeah, I find it easier to think of it as the hypothesis space in which you're wandering and looking for the best hypothesis, right? But that word is not commonly used. The more commonly used word is the parameter space. Go ahead.
Is the path from HA to B, is it going to be straight all the way?
No, it won't be straight. It will vary, right? So it will be a curve kind of a thing. Now in linear regression, life is very simple. But actually, when you come to more complicated situations, it's sort of a zigzag path, gradually come to it. Also, the whole question is, we are this kind of gradient descent that we're talking about. How do we look at the error of the entire data set at each step, or small batches of data and so on and so forth? So there are all of these notions of batch gradient descent, mini batch gradient descent, stochastic gradient descent. There's more complications to that, right? But let's focus on the key ideas today. And then there's more happening there under the covers with this. So now I would like to say that we have covered two big ideas. We say machine learning is quantifying error. For regression problems, sum squared error is a pretty good way of, a simple way, linear regression without, these are called ordinary least square regression. Like you will realize that I will change it a little bit. It gets more, new nuances keep coming in as we move and do regularization, etc. But for simplicity today, error is what you minimize. When you are minimizing the error function, the best way, the fastest way to do that is using gradient descent, right? And when you do gradient descent, it will take you home. So you quantify the error, you minimize the error. Minimization of the error is the learning process. The learning of machine learning is the minimization of error, which you're doing here using gradient descent, right? And that is the heart of machine learning, guys. Huh? So this is it, guys. I will just is there any point that I need to? Now, this is a lot of big ideas that I brought in. I will just summarize. I don't know if I need to summarize. I will repeat some of these ideas in the next session. And by the way, all these handwritten notes I'm going to post to the class discussion group, so you can read my scribbles, right? It will be there. With that, if you don't have, does anybody have questions before we take a lunch break? Not everybody is hungry. Okay, folks, so it is exactly 2 p.m. How long a lunch break do you think we should take? After that, there is 3-4 hours of lab. Should we take an hour and a half of lunch? 90 minutes, is it okay? Or 2 hours?
30 to 40 minutes is good.
I think 1 hour should be enough.
90 should be good. 90 should be good.
Yeah, no, because some people have to, how many of you have to go to the restaurant to get lunch? Only one person. So those people who are going to a restaurant, give a realistic time. Okay, almost everyone. So the restaurant people give a realistic time. How much do you need?
I think hour and a half. Like it takes
Hour and a
20
half.
minutes to-
Let's go to a fast food place. Maybe
Yeah.
go grab and come.
Yeah.
Something that will get us back quickly. So,
When you don't sleep.
No, don't do quickly because you have a long 4-hour session.
no, but food is thing. So they get in and out
Okay.
faster.
Yeah, if you can take out and bring it here and so forth. So 60 minutes or 90 minutes?
60 is good.
90 should be good generally.
90 should be good. Huh? All right, 90 minutes. Let's go with 90. I don't want to start with the half the people missing.
Isn't that guy of his house?
All right, folks, welcome back from lunch. We will continue now to the lab part. As per our lesson plan, today's lab will focus on linear regression and some variations to it. We will devote the next couple of hours to stepping through carefully through a few data sets. We will be dealing with the data sets shortly. But before we do that, there is a small visualization, the two visualizations. One Kyle created and posted to Slack. I don't know if you noticed it, a very nice plot of 6 figures, 6 subplots that shows you how correlation varies for different values of different value. I mean, how the graph, how the data looks for different correlation values. Now, here is a little visualization that where you can see, this is all in your code. When you download it from the lab, the guided lab section, you will get a file called correlation.pgz. Just unzip the file and read the README. Now, I'm going to, at this moment, just show it to you, but at some point, do make sure during the break that you play around with it yourself. It's a little visualization I created. And if you look at the screen, as you change the correlation row, the data seems different. So for example, when you go closer to 0, the data shows no relationship. Do you notice that the data at this particular moment close to 0, it is just looks like random data. It has no relationship. X and Y are unrelated. For any value of X, Y could be anything, right? On the other hand, when you go and have a strong positive correlation gradually, it becomes more and more stronger related. Now, I encourage all of you to please try out this visualization. It gives you a very good idea of the basic concept of correlation for data. Remember, if there is correlation, there is a relationship, linear relationship. But absence of correlation does not mean there is no relationship. Right? So we talked about that, just to review it. Now, with that being there, this application that we use, it's very popular. This library is very, very popular amongst data scientists. It is called Streamlit. It is a data scientist's dream. You don't have to learn React. You don't have to learn Angular. You don't have to learn the whole web technologies. You can write your UI in interactive UI in Python, just a few lines of Python, and run it. And lo and behold, you have a perfectly good web application running. As you can see, this is running on Kate's local machine. You can therefore quickly create the application. If you look at the code, it's a, I suppose at this moment, I'll take over and share my screen. And this. And oh no, not share that screen, sorry. Yeah, I will share that screen itself. But is that better? Yeah. So if you go into this, whenever I give you a zip file, you will always find a README. It is customary in our field to create directories of code or notebooks and then have a README file there. These README files are typically written in Markdown. What it says is, this is pretty much, and to run it, you need to give this instruction, streamlit run main.py, right? So if you give this thing on your command line, you can run it locally. I won't do that. But I will now start with the 3 data sets that we have. The first data set is, okay, so please download these 3 data sets from either the internet, from the class course if you want to keep it locally. Otherwise, you don't need to. It is available in GitHub. You can directly load it from GitHub without needing to download it. So I will now go through the.
I think the Zoom you're not sharing.
Zoom is not sharing this. What is Zoom sharing? Oh, so I'll stop that again. Actually, let me do one thing for the duration. No, okay. Sure. Yes, I'll do that. Let's see what it takes to make it look better. Is it now readable? Little
Yes.
more. Is this better?
Yeah.
Okay. So, folks, we are going to take a simple data set. It is a univariate data set, means there is one predictor and one response. X is the predictor, Y is the response. And we will go through the traditional data science approach. We'll just do it methodically. And this sort of a methodical approach that you will learn here, I would encourage you to always use in practice. Go very slowly, methodically through data. Now, this is the outlines. As we advance in this course, in this workshop, I will add more and more to this method, this data analysis pipeline, but we'll start with the basics. Now, typically on my machine, on the Linux, I have set certain style sheets, which obviously you don't have, but just so that it looks, and of course on this laptop isn't there. So what I've done is the first cell you can ignore. It is just some HTML styling for the page. You can ignore that. So let me make sure we run it. Yeah, so this is it. Now, sorry, I gulped down coffee. This data set is available on GitHub. support vectors ML100. You'll see a lot of data sets there. In the course of this workshop, you will be analyzing all of them. But for now, we'll start with one simple one, univariate one. Right? This particular data set is quite a simple one because we are starting to learn how to do it. As we analyze this, and the two things we'll do, we'll build a exploratory data analysis, we'll visualize the data, learn to visualize the data, and we'll also learn to build a simple linear regression model on the data, right? So what are the goals for this lab? The goals are, we will explore this data, observe its statistical characteristics, you understand, all of the basic descriptive statistics, and visualize it. That is one goal, which is the exploratory goal. The second goal is we will take a systematic approach to build a regression model and then use it to make predictions and then see how good those predictions really are, right? So those are the goals of this lab. What is the outcome that I'm hoping for? What is it that we plan to learn from this? My hope is that at the end of the lab, we should have an understanding of the following, each of these 8 items. What is a data frame? Right? This is a concept we'll learn shortly. How to load data into a data frame and describe it. How to use the pandas profiling to get some basic understanding of data. It's a library that's quite commonly used these days. How to visualize the data using Matplotlib. It's one of the data visualization libraries. And then next onwards, so the first 4 are data explorations. Then we build a simple linear regression model. We will learn how to do that. We will learn to do residual analysis of the model prediction. We'll learn about it. These words may not mean much, but will mean something after a while. Model diagnostics. Is the model good or bad? How do you determine that, right? And finally, can you confirm the quality of your model by making predictions and visualizing those predictions? Now, these steps that I write, all of these steps, all of these things, these are crucial to data science, basic data science. So we'll start with it one by one and make progress. For those of you who are remote, let me know if you're able to see me. Are you folks able to see me?
We can see your screen.
Oh,
Yeah.
but you can't see me there. Okay. In a box or somewhere. Oh, I should be visible. I don't know what happened.
So when you move to the,
Yeah, we can see you.
you're not visible there.
Oh,
Yeah, we can see you. Yeah.
we can see you. Unfortunately, my table's arrangement I have to fix. I apologize that I'm visible in a corner of the screen, but okay. So what we do is, first step is to import the necessary libraries. What happens is your notebook is running as a process, and basically the libraries of Python that you will use, you need to sort of bring it in, right? And by looking at the import at the end of any Jupyter notebook, you can often get a sense of where it's all leading. So I will line by line explain what each of these means. So we start with some of the standard imports, which you are likely to do very, very often. One of them is NumPy. NumPy is the library which gives you, amongst other things, the n-dimensional array. Arrays and matrices, right? And higher dimensional arrays, they come thanks to the NumPy library in Python. Now, the NumPy library has a lot of hundreds of functions, very, very useful. You can spend months gradually mastering them. But at this moment, and for quite some time, we'll just focus on just the ability to create arrays of data. Right? So that is that. Pandas. Pandas is a library that gives us a representation, a standard representation of data, which is more or less a canonical representation, sort of the way data scientists think of data when they're doing analysis. This structure, this data structure is called data frame. The easiest way to have and intuition about data frame is to think of it like a single sheet of spreadsheet, single spreadsheet, not with multiple tabs and this and that, just a simple rows and columns. Another way to think of it could be like the results of a SQL query, rows and columns in a database, right? But it is not just a sort of an inert repository of data in a rectangular form, rows and columns. A pandas data frame is more than that. These data frames typically come with a lot of functionality built in. They help you manipulate the data. They help you do descriptive statistics and other things with the data. A lot of conveniences and functionalities built into a data frame typically. Right? Now, data frames are the foundational unit, whether you're doing work in R or you're doing it in Spark, you're doing it in Python, everywhere, the word data frame, it is part of the sort of the vocabulary. The first statement that people will say, have you loaded? How is the data looking? And how does your data frame look? Or how does it look? Just show. Right? So we'll use that. Then the next are the pre-processing libraries. Obviously, it's a little overwhelming here. If it is too much of new stuff at this moment, you can ignore some of it. See, when you train a model, how do you know that your model is good? Model algorithm has seen the data. How do you know that it hasn't just memorized the data? One way to do that is to hide some data sort of under the pillow, not show it, right? And give it only a subset of data to train from. When you give it only a subset of data to train from, and you hide the rest, later on you can ask the model to make predictions on the rest of the data and see the predictions that it is making, the y hats, how closely does it agree with the y? You can then look at the residuals, just as we did. We talked about it a little while ago before lunch. So we'll do that. So what you do is you take the data and you do some sort of a split, 70-30 split, 75-25 split, or 1/3, 2/3 split, whatever is your favorite number, 50-50 split. You can split the data, keep and hide half of it. The part that you hide is called the test subset of the data or test data. People just say test data. The part that you give to the algorithm to learn from is called the training data, right? So we will split it into just two parts. More sophisticated way would be to build it up into 3 parts and so forth. But here we'll just break it up into 2 parts. You also notice that there is a standard scaler. Remember, we talked about z-valuing things with the random variables. You convert them into the z-valued equivalents. Right? So the standard scaler does that. It helps you do that. It so turns out that in this lab, I decided, in the interest of simplicity, I didn't scale the data. And for linear regression, you can get away without scaling, but you don't get away without scaling for a lot of other algorithms. So we'll let the scaler be there, but I thought I'll mention it. Then you have something called polynomial features. Why we need that, you'll see in a subsequent lab. And also make pipeline. You can ignore the polynomial features and make pipeline for now. Just the most important thing to remember is the train and test split of the data. Then,
So Asif, quick question. So what is the difference between the train test one and the data frame itself? In the data frame as well, we can split it, right? So
yeah. So when you get the data frame, it has so many rows and so many columns. So what you do is you take a random number of rows and you consider them to be the train data. You create so you divide a data frame into two data frames, 2 subsets. One data frame you call the train data, the other data frame you call the test data. And basically it is built out of the original data frame by breaking it apart into 2 pieces. Right? So some rows go into the train data set and so the rest of the rows go into the test data set. Right? And all those data sets are data frames. Does that answer you?
yes, sir.
Yeah. That is it. It's a very simple thing. You just chop it off. The only thing is that you don't want to do it sequentially. You don't want to say, okay, the first 2/3 rows make it train the last 1/3 row, because there may be a pattern in the data. For example, data may be sequential by chronological order. So what test train will do is it will do the shuffling. It will randomize it, make sure that you get a random selection of the rows. So that is what it is. Now comes the, where am I? Give me a moment. Yes, so next we go to linear regression. See, today is the day we are going to learn linear regression. So this is what we have been talking about, simple linear regression. This is it. Now, when we said that we are going to look at errors, how much error is there? Do we recall that we talked about the mean squared errors? Right? Mean squared error is the sum squared error divided by the number n, the number of data points. That's the mean squared error. And the R2 score, can you guess what that could be? R2 score gives you the R squared, the coefficient of determination. We talked about that, if you recall, right before lunch, the coefficient of determination. So these are two key model diagnostics to get a quality of fit, a goodness of fit of the model to data. We'll look at that. Then comes a lot of graphic libraries. Why is that? Data, visualization data of the data is very crucial in this field. Sometimes a lot that you can literally, when people say a picture is worth 1,000 words, it is very much true here. Sometimes you may do all sorts of analysis and this and that and get a sense of the data, but the right approach is to also include visualization and emphasize visualization, because a human eye is a massive computational engine, well evolved over 100 million years. It grasps things in the blink of an eye, literally in one single glance. It absorbs a lot and sees a lot and learns a lot. So you do want to have very rich visualizations here. So in this field, plots, graphs, etc., diagrams, they're not just sort of pretty things. They are at the core of the subject. Data science, a lot of emphasis you put on data visualization. So the default data visualization library that comes built in, that most people use when they do this thing, Python-based data science, is matplotlib. And Pandas is a very, very simple and direct integration with matplotlib by default. Right? So that is one good thing. But generally, the criticism of matplotlib is that the default plots that it makes are leave a lot to be desired with respect to the aesthetics. They don't look as lovely or as striking as the plots produced by other libraries. So here I'll show you some other libraries. One of them is Seaborn, and the other is Altair. These are libraries which bring their own virtues. And it is good to be familiar with 2-3 data visualization library. Start out with matplotlib and then gradually venture into other ones. Then these things, by the way, are a little advanced things. What happens is it goes to the aesthetics. When people make diagrams, or it is my habit that whenever I do that, I tend to be particular about what the size of the figure should be. The default values won't look good. I want all my figures to be the same size. I want the fonts to be a certain size. I want the label fonts to be a certain size. So these are just basically styling parameters. So you can ignore most of these styling parameters. Right? And lastly, go ahead.
The set option plotting backend matplotlib.
So, sorry, which line are you saying?
The pd.set
Oh,
option.
yeah. So one of the things with Pandas is the backend, you can set it by default, it is matplotlib. You don't need to say that. But it also has integration with another library called Bouquet, another library called Plotly, right? Python world, the thing is, there's so many data visualization libraries, it gets a little bit overwhelming. And everybody will come and say, my library is better, right? My general recommendation is first master matplotlib, which is why I changed the default to matplotlib. It was the default. Actually, that line of code is not essential. But if I put instead of matplotlib, if I say plotly, then it will start rendering things in plotly. The matplotlib has a simple syntax. It looks, but it takes effort to make it look beautiful, which is why you see me do all sorts of things right below it in an effort to make it beautiful. Now, one of the things you do, because I make diagrams which go into some technical reports in my work, and like into articles that I write and things like that, there's a general feeling in the community that if you write something formally, you cannot write, pay a lot of attention to the text and what you're writing in your equations and data, but create substandard plots, substandard graphs. It must look aesthetically pleasing and professional. So I tend to use something like text labels, etc. I tend to use LaTeX for. The LaTeX is a typesetting language, by far the best. It's the work of Donald Knuth, the great god of this field of computing. His classic is The Art of Computing. And I invite all of you to go browse through those lovely volumes. So anyway, LaTeX is what people use. Most of the scientific, or most of the papers written in our field, in any of the mathematical fields, are written using LaTeX. They are typically not written using Microsoft Word or, I don't know, Google Doc or something like that. People typeset it beautifully with LaTeX. So LaTeX, though, needs an installation. Kyle put those installation instructions for Windows, those of you who have Windows, God forbid. But if you have Linux, it's a very simple install. If you have Ubuntu, you can just say apt install TextLive or something, and I can put all those instructions there, and it will install the whole the text system there, like LaTeX and everything else. On the other hand, if you have, the same applies to Mac, very simple and clear instructions. Guys, be a little bit not so loud, all of you. I wish not so loud. Okay, so LaTeX is something, at this moment, I would say that if you are working, if you're not familiar with it, do you see this line of code? It says true on my screen. Do you see where it says use LaTeX? Use text, guys?
Yes, yeah, yeah.
Yeah, so I would say that unless you have LaTeX and you're familiar with it, mark it as false. Right. So then you don't have to worry about it. You don't have to worry about installing LaTeX or anything like that. Right. So by the way, how many of you are familiar with writing LaTeX documents? A couple of you are. Okay, so few. So yeah, it's just a more professional quality things. The next is just setting the font size and so forth. Import warnings. What happens is when you run your cells, Python libraries, they throw a lot of warnings and messages, and often it becomes a clutter. It clutters up the notebook and degrades its aesthetics. If you know exactly what those warnings are and you feel very comfortable ignoring them, and then you add these lines. Otherwise, of course, you should pay attention to the warnings. I've done that. Then what you're looking at is something called a Jupyter notebook. We talked about this notebook last time. I hope I took you to the place at which we could launch the notebook and do things. What I would encourage you to do is, anyway, that's part of your homework. You'll have to create a few notebooks for a few data sets. I have here given you the analysis for 3 data sets. There are 8 data sets there. Of the 8 data sets, 3, I'm giving you notebooks. The rest 5 are your homework. Are we together? So, and please do take the homework seriously, guys. See, at the end of the day, however hard the teaching staff here works, if you don't put in the effort to do the lab, it all goes waste. Because it is practice that drills things into your mind. So this week, please do those labs. And when you do the labs, remember, we are there to help you. Reach out to us. Once you finish the labs, come to us and review. I will be releasing the solutions to these labs at some point when all of you have tried. If all of you don't try, then I will not give the solutions out. Right? So this is a thing, incentive. If you all try and do the labs, I will release the official solutions, otherwise not.
I see one quick question. So the data sets that you're referring to is on the GitHub page,
All on the GitHub page as well as on the course page.
and 3 as classifiers and 5 with the prefix.
No,
data.
forget the classifier. So the course, so anyway, we'll come to that. Hang on, the homework is mentioned here. Anyway, since we are jumping ahead, I'll just mention in one of these notebooks, you'll see your homework. You need to analyze these data sets, these 5. That's your homework.
Okay.
Right? And if it helps you, it is repetition to a large extent is repeating what you have learned, what you are seeing today, but doing it for different data sets. But when you do it, don't do it blindly. I have created these data sets after very careful thought. They have been designed to teach. So each one of them has its own unique lesson to teach. It isn't that it's just 5 data. Here are some 5 things and you just practice on them. Each of them has an element of surprise. Each of them has something new to teach. Are we together? And as you analyze it, you will learn it. In the 3 data sets that we are going to do today, you will realize that each data set teaches you something very specific. Are we together? And we'll see that. And so the rest 5 also teach you something very specific when we come to that, when you do that. So please do try it. Otherwise, what happens is if you just see the solutions after a little while, you lose confidence that you can do it on your own. This is very easy stuff, actually. But so our journey starts with loading the data. So let us load the data from the specified URL into a pandas data frame. You have 2 choices. Either you can load it from download it to your local machine from the course portal, right? All of the links are there. If you click on it, it will download it. So you can load it locally. Pandas has a lovely function called read CSV. And the argument to that, the source could be your file system, C:, blah, blah, blah on Windows, right? Or it on Linux, it could be / home and whatever, home, your home and the data, or it could be just a remote URL. And that's the beauty of it. In this case, I don't bother to download it. It is just coming straight. I'm just reading it straight off GitHub. Okay. So this is a way to read the data. When you read the data, you just have to say data.read CSV. Is this thing clear? Easy to understand, right? Simple and elegant. One line will load the data. CSV is, of course, comma separated file. Each row of data, the field values are comma separated. Okay. Now, in Pandas, part of the convenience method is, now you have a rectangular data frame. You out of curiosity, you would want to look at the first few rows or the last few rows, or just a random sample of rows, right? It is always a good idea to just preview the data, always preview the data, see if there are surprises, right? This is essential if you, by accident, download the wrong data, right? It has happened in production and real life, it happens all the time. I've had developers come into me, yes, we put the right data in and this and that and so forth, and the results are not coming. And sometimes the silliest of the reasons would be there, like the wrong data is being fed into the pipeline. So always preview what you fetch. Right? So preview the data. Now this method head will give you the first few rows, the tail will give you the last few rows, and it will typically give you 5 rows, but you can give n. By n, you can choose, like give me first 20 rows. So just say head 20 or tail 20. So here, if you, like I said, head, and I'm not giving any argument, so it will give you the first 5 rows. Will you see that, guys? You have the first 5 rows of data, right? So from this data, right away, it is obvious that we are looking at a 2-dimensional, like basically 1 variable X and 1 Y, univariate data, 1 predictor, 1 response, isn't it? Well, that is your interpretational thing that we are doing it in view of the discussions that we are having before lunch. You can look at the last few rows by saying tail. By the way, the word head tail, it comes standard from Unix. If any one of you works on Linux, you must be very, very familiar in doing head tails all day long. Data.sample will take random samples, right? And there are more nuances to it. It's like sampling with replacement, without replacement, and so on and so forth. There's more to it, but let's keep it simple. I got the 5 rows from here. Now, once you get the data, one of the first things you would want to do is do a descriptive statistics on the data. What is it? Remember, we do a descriptive statistics. Each of the statistics is like, how many data points are there? Mean. What is the mean? What is the, well, in this case, I haven't done the median. I leave it to you folks as an exercise to find the median of the data for what it matters. In this case, it's not terribly relevant, but why not? Mean, standard deviation. What is the minimum of X and what's the maximum? So what is the range of X values? 0 to 10, right? What is the range of Y values? From -11 to 92. Right? That's the range of the data. So it gives you some gut feeling for this data. Do you notice that the standard deviation of Y is significantly more than the standard deviation of X? Isn't it? So Y is more spread out. The values of Y are more spread out. Now, one of the things, and it's a nuisance, but a fact of life, that whenever you get a data, sometimes it will have holes in it, right? So certain rows, certain cell values, or certain predictor values will be missing. Right? So it's a part of life. So I'll just read out this thing that I wrote for you and tell me if it is further discussion. Oftentimes, the data set will have missing values. Certain instances of data will have one or more, it should not be off, or more features missing their values. This can happen for a variety of reasons. For example, a value there may not make sense. For example, if you have a data set on mammalian animals, one of the features may be the length of the legs. So when we think of mammals, most mammals come hopping to us on 4 legs, isn't it? Right? So, well, a dolphin is a mammal, but it does not have legs. So, in the traditional sense, therefore, a datum representing the attributes of a particular dolphin will have missing values for the attributes specifying the length of its leg. Would you agree with that? There's no way you can do that. It's missing value. So that is an example of missing value. Another common reason could be that that specific feature, while it could have been observed, happened to not have been. Right? So somebody forgot to take measurements. Right? Oh, right? An example could be the number of fireplaces in a house when looking at a housing data set. Right? And we'll encounter this in a little bit. Right? So in this data, let us check if there are any missing values. So you look for those rows of the data that have null values somewhere. And then you see how many of them are. It turns out neither X nor Y have missing values. Right? So this missing value analysis is sort of moot here. It makes it moot, but you will know it only after the fact, after you have checked it. You wouldn't know beforehand. Right? There is an excellent library called Missing Null that presents the information visually. Once again, here, it is not very informative because there are no missing values. All it says is there is no missing values. But this bit of code, you'll find it terribly useful when you deal with data that does actually have missing values, right? So it shows that all the data, all 1,000 points of data are just fine, right? So we don't need to worry about missing values. So if there are missing values, what do? Then you have to do the missing value treatment. It is called attribution. You need to attribute some value there. You can put an average value. You can take the value of the previous record and stuff it there. You need to find some sensible way to fill the holes, right? With data. Otherwise, you won't be able to work with the data. There is a useful tool called pandas profiling. So if you give this command, pandas profiling, in one shot, it will produce for you a lot of data visualization, which here I don't see. Maybe I'll have to run this to get it. Oh goodness. Okay, let me start running this. So I don't use this laptop for actual work. I use it only for teaching. So obviously none of this has been run here. Oh, obviously pandas profiling is not installed on this machine. So forgive me, I won't run this code here because it won't. Then maybe next time I'll bring the Linux here. What's that? Yeah, why don't you share your screen and show this? In the meanwhile, let me go and insert a cell and see if I can Let me stop. That's right. Yes.
Takes about 20 seconds to run.
Yes. So when it runs, it produces a lot of sort of data explorations. It will tell you quite a few things. Like if you look at the overview, how many variables are there, missing cells, etc., etc. It will also give you, for each of the variables, all sorts of statistics. For example, how many distinct values are there? Are there missing values? And do you notice that the histogram of X is uniformly distributed, right? The X value seems to be uniformly distributed. What about the Y value? Does the Y value seem? It seems to be more centered, a little bit. And let's scroll down. And you can see, by the way, all the descriptive statistics. Do you see that standard deviation, kurtosis, mean, skewness, variance, etc., etc.? All of those things are present here, right? So these are all examples of statistics. So interaction is not very informative. We can move on. Correlation. So it says that, well, X and Y they seem to have a certain degree of correlation. In fact, a very high degree of correlation. What does blue signify? High values of correlation. Are we together? So which means there is a linear relationship between them. All right, let's scroll down. So missing values, again, no missing values, right? A first few row sample. This is your head, pandas.head and pandas.tail, basically. And let's keep going down. Thank you. That is it. So Kate, from here, I'll take over. Thank you for this. And while it is happening, let me just start this. On this laptop, I need to have it profile. So let me get this going. Right. So as we go through, where are we? So missing value treatment we did, pandas profiling. So now comes the point about visualizing the data. We need to learn something about how to visualize data. Beautiful thing is that if you need just simple plot, quick glance at the data, most of the time you can do visualization with one line of code, right? Just one line of code suffices. So for example, here we want to make a scatter plot of the X and the Y in the data frame. So do you notice the syntax that I'm using? Data is the pandas data frame. So going back at the top, you must have noticed that I read the CSV file into a data frame called data.
Asif, we can't see the notebook.
Oh, you cannot? So what exactly am I sharing? Once again, I'm sharing the wrong thing.
Oh, the navigation.
Yeah.
Oh gosh, I apologize. So thank you for pointing that. So, all right. So the point is that we need to do data visualization. The first library we'll use for data visualization is matplotlib. The visualization, I hope you would agree that it could not get simpler than this, right? One line of code does it. Now, some people with Python say, why are you putting semicolon in the end? Isn't that something that people do in C, C++, Java? Why semicolon here? There's a reason for it. It turns out that if you don't put a semicolon here in a Jupyter notebook, it will just put some junk in the beginning before you see the actual plot. To suppress that junk, you just put the semicolon and it keeps it clean. Otherwise, you see some clutter here. Now, data in square brackets, you give the name of the feature. The features are X and Y, right? So you give these features and then this data comes up. Just one glance at the data, you can see the high correlation, isn't it? You get a strong sense of the data. Literally, you look at it and you feel like drawing a straight line through it, isn't it? You feel like taking a marker and drawing a straight line in this data, right? You can see the relationship. And that is the power of the human eye instantly grasps what is it that you're looking at. Now, which is very useful when the data is one-dimensional or two-dimensional and so forth. But gradually, you will encounter data in higher and higher dimensions. Unfortunately, much of the data that we encounter in machine learning these days are so high dimensional, it's mind-boggling. Typically, we deal with data in 500,000 or million dimensions, or 3 million dimensions, right? So we will get there gradually, but as again, we learn to crawl, walk before we run. But the principle is the same everywhere, right? Wherever possible, do visualize the data, right? Do remember to visualize the data. And so when we visualize the data, here are some observations. Whenever you visualize the data, do note down your observations. It's a basic thing. It's a scientific discipline. Observe that the data appears to be linear with a positive correlation. Would you agree with that, folks? You would, right? The plot of the data in its default form leaves some scope for improvement. So for example, if somebody just got this plot, do you think they can make anything out of it? They don't know what the x-axis is. They don't know what the y-axis is. What is related to what? There is no label. There's no title, isn't it? And frankly, even from an aesthetic perspective, something could be better. So the title, X label, Y labels are missing. It could be more aesthetically pleasing. And then this is the optional part. If one would like production quality labels and title, one can use the power of LaTeX typesetting too, right? So that at this moment, you can do it if you feel like doing it, otherwise skip it. In the below code snippet, we have added some basic aesthetics. So all I did is that line of code, one line of code, I have now added more to it. And this is sort of the difference between quick and dirty versus being polished. Typically, it turns out that for graphics, those of you who do user experiences or who are in graphic art, you know this, that it takes a tremendous amount of effort to create a polished picture, right? And that is true in this data science also. You'll often see that while visualization code is relatively easier, you spend a lot of energy doing it, a lot of time doing improving the aesthetics. So I'll explain every line. You notice how the points are solid red here, right? Just a little bit. I don't know if you would agree. Would you agree that this looks a little bit more muted, more aesthetically pleasing?
Yes.
Yeah. So the way I did that is by making those dots a little bit transparent, right? Alpha is the keyword for opacity, like transparency. People in art often use the word, what's the alpha channel? How much is the alpha value? The size of these dots, I increased it to 150. And because it was red and red was sort of strong on the eye, I sort of muted the red down to salmon color. Now, beauty is in the eyes of the beholder, so each person's aesthetic could be different. But generally, I'm just giving you a sense of how you would do it. So these three attributes just made it look a little bit, hopefully, aesthetically pleasing. But then I added the title. Now, this looks like a very complicated, a very arcane mantra out here. This belongs to the language of LaTeX. You don't have to do that. You could have just said a scatter plot of X versus Y or Y versus X, simple text, right? But this is in the language of LaTeX, so it may look as scary, but you don't have to do that. This is optional. But what it does is if you do it, do you notice that this looks, how does it look? Does it look very textbooky? Right? This is how things are there, for example, in ISLR, isn't it? That because ISLR itself is written in LaTeX. So, or I think so. Yeah.
So in the second, what does it mean the dollar Y dollar versus?
Oh, those are LaTeX syntax, Sanjeev. At this moment, let's skip it.
Okay.
Yeah, those are mathematical notations in LaTeX. So do you notice that the X looks in a different way? It doesn't look like normal text. It is the way you find X in math textbooks. So dollar makes it a mathematical variable. That's all.
So as if you print a title, you just use that same command and just change the text.
Yeah, just embed LaTeX into it. And which is one of the niceties of Matplotlib, that it has such a good integration with LaTeX. So, well, this is it. Now, there's another Yes.
Is that an integration of Matplotlib with LaTeX or with Jupyter with LaTeX?
No, Matplotlib with LaTeX.
Oh, because it's brought it up in this.
Yes. So you could have saved this plot to a PNG file and could still have all of this formatting. Another very popular sort of library people use, and often you'll find code for this in Medium, etc., is using Seaborn. Seaborn uses Matplotlib as a base, but its claims, its main thing is that it makes it easier to do some tasks and it puts a more pleasing layer on top of it. So just out of the box is supposed to be a bit more pleasing, though in this particular case, probably not, right? So here is the same graph using Seaborn. I won't go into that. You can read the code and this thing. Yet another library. So this is a static. Both Matplotlib and Seaborn, they produced a static image, a plot, right? Sometimes people like a bit of visualization makes sense. So in the visualization world, one of the big things that has happened is there is this lovely, lovely library, which is called D3. How many of you are familiar with D3? Some of you are, right? So D3 is actually created by Michael Bostock, and it has become a runaway success. It's become the de facto standard now. So many libraries, but it's a low-level library. So many people have written libraries on top of D3 to make it easier, quicker to work with. One of them is the Vega Lite. Again, a JavaScript library, just like D3 is a JavaScript library. Well, we are dealing with pandas. And then we are dealing with Python. So somebody had this excellent idea. Why not put a Python layer on top of Vega Lite, right? Vega library, which is sitting on top of D3, so that in a few quick lines of code, you can produce what would take a lot of code to do in just raw D3. And you're doing it in Python rather than JavaScript. So this is it. This is Altairs. They're creating a chart with circles of certain size, X, Y. I hope this code is self-explanatory. You're going to mark in the scatter plot, you're marking circles. X is X, Y is Y. Tooltips you're given. You're giving a property. How much will the size of the image be? Oh my goodness, I did not run it. But if you had run it, where's the output? There's Ashwin. If you had run it, if you run it on your local machine, on my machine, I'm having all sorts. Actually, it might have installed. Let me go and see. Things may have installed. Yeah, just bear with me here. What just happened? No module name pandas profiling. It's still failing. Okay, yeah. No.
But you didn't install Altair.
Yeah. Oh yeah, it succeeded. So now let me run this thing from the beginning. Just bear with me for a second, guys. I will run only the key sections. Okay. And I'm not going to run the pandas profiling because that may take quite some time. So I hope, okay, let me just run the crucial sections. I need to load the data. There we go. Head, tail, descriptive statistics, I'll assume it's all there. Pandas profiling, I'm not going to run because it will take time. Let's go and run to the data visualization plot, scatter plot, Seaborn, and Altair. Let's go and try a lot with Altair. Yeah. See, when you look at the graph generated by Altair, do you notice that it's dynamic? I can look at the tooltips. It's a very basic amount of interactivity because ultimately it's just a couple of lines of code. But one more thing you notice about this. You notice how you can zoom in and zoom out, right? You can just pick, you can move it around and so forth. So this is a full-blown dynamic, interactive graph. So that is the beauty of it. With Altair, you can do that. In fact, that correlation, interactive correlation that you saw in the Streamlit, right, that graph I had generated using Altair. That code. And by the way, the source code of that is available to you in the download. You can read through the source code, all of you, and you'll see that it is. Right? If you want to understand that source code, please do sit with us, any one of us, and we'll explain it to you. So that is about data, exploratory data analysis and visualization. Our next goal is to build a regression model out of it. Right? We want to build a model that relates X to Y. Y is the response variable, a target variable or the output variable or whatever, and X is the input or the feature or the predictor. These are all synonymous words, as we talked about. So we'll do that. And it is quite simple, actually. The first thing you need to do is in Python, like you use a library called scikit-learn. The fundamental machine learning library that is most popular is scikit-learn. This scikit-learn expects that you separate out the input and the output. In this case, what is the input? X. What's the output? Y, right? So, but then it expects the input to be a multi-column data frame. It expects it as a pandas data frame, right? So, but output it expects as an array response variable. So that explains this data's X. When I remember, do you notice this double square brackets? It is basically saying create a pandas data frame, another data frame called capital X, right? So capital X is this, and little y is this. Okay. Now, there's a lot happening here. First of all, notice, guys, that you could not have used the syntax in other languages like Java or C, right? You can't write the syntax, it's not valid. What it is saying is capital X is equal to the first term here on the right-hand side, and little y is equal to the second term. Now, this double bracket is just creating another pandas data frame, which happens to have only one column called X. Right? This is it. Now, another thing that you, so I'll just read out the part that I wrote. Let us build a simple linear regression model for this data set. In order to do so, you go ahead.
So the double one is getting so the capital X is a data frame, and how about the small y? It's a series.
Small y, the small y is just a, yes, think of it as a series or a array. It's basically a one-dimensional array.
Okay.
Right. And so because, response variable is just output number, right? One number. Whereas input could be many things. Many features may go in to predict that. So I'll just read this. So this syntax, now there's more here, guys. It is customary in this field to use capital X for input, a data frame, and little y to this. We could have named this variable anything, PQRS, cat, dog, whatever. But it is a convention in the field that you give these names to input output so that it becomes very easy for people to read your paper. Remember when I was explaining to you in the earlier session, morning session, what did I use for response variable? I used little y. Do you remember that? Right. So it is a convention in our field, in this field to do so. Right. So hold on to that. When you follow conventions, it becomes easier for other data scientists to understand your work. Our next thing is we want to split the data into, remember, a training set, and test set. Test set is the one that you sort of hide under your pillow in a metaphorical way. Don't let the model see it. Don't let the algorithm see it when it trains a model, when it trains itself. So what you do is very simple, actually. You take an algorithm. Here, we are taking a linear regression as a model, as an algorithm. And then we are fitting the model to the data. So the fit is the train part. It is the learn part. It will go learn from the data, but not the whole data, only the training data, subset of the data, right? Now, just for your recollection, whatever we talked in the theory part today morning, I've written it here. So Y is made up of the part that is the actual model plus epsilon. Epsilon is your irreducible error. Remember, irreducible error comes from those things that the data didn't contain but are effective of the response. But it also contains other things like instrumentation error. If you take a very sensitive thermometer and you measure the temperature of the same thing, you will realize that it sort of fluctuates. Right? There's a lot of error in that. So measurement error, et cetera, right? And sometimes people actually make measurement errors. So what I have done here is model is built. Then let us look at the intercept and the slope, because what is the model? Model is this. This is the model, right? So it will have an intercept and it will have a slope. Let's go and see the intercept and coefficient. So anything beyond the beta naught, these are called coefficients in the language, in this sort of way of thinking. So our intercept is minus, well, very small, 0.1, minus 0.1. A slope seems to be 8.3. Now let us see, does it make sense? Would you agree with that? Let's go and look at the data. Or any one of these, let's say. I don't know, pick one. Let's say pick this, the latest one. Would you say that in your mind, if you drew a line through it in your mind, it would be around close to 0, minus 0.1, so close to 0. The intercept seems to be 0. Is that fair? You agree, right? If you build a model, imagine a model in your mind, the intercept will be close to 0, right? A little bit negative to 0. And what about the slope? We can find the slope very easily. For unit increase, let's say from 1 to 2, that is 1 unit increase of x, how much did the y increase? So here the y seems to be approximately, what should we say? Would it be reasonable to say a little less than 10? Right? And here y seems to be a little less than 20, right? Somewhere here, maybe 16. So let's say that it was 8 and it has gone to, so 1 unit increase, it has increased by about 8. Seems right, isn't it? 8, 9, 7, 8, 9, right? Something. So the value, and this is important, guys, that never trust the code. Always go and verify that what you find makes sense. Here it seems to make sense, right? It says intercept is very small, practically 0. Slope is about 8.3, right? So give or take, your own eyes may have said, well, somewhere between 7 and 9 or whatever it is, right? So it does seem to agree with your estimates. Now that you have a model that you think might be of value, let us go make predictions. But make predictions on what? Not the training data where you suspect it will do well, but you test it on, preferably, the test data, right? The testing data, the data that you hid under the pillow. When you look at the testing data, you will get what? Y hat. Remember, in our morning session, we use the notation Y hat, right? So obviously in code, we can't make it Y wear the hat on top of it. So we literally spell it out as Y hat. And so it says that the mean squared error is this 32.46. But look at this, the coefficient of determination is 0.9476, close to 95%, right? That looks pretty good. Remember that the maximum value it can achieve is 1, isn't it? Given the fact that the noise does have some, the data does have some noise. You can see the noise, right? There's some irreducible noise. A value of 95% approximately of R square seems fairly good. We seem to have built a good model quickly. So now what happens is, this is where most people stop. In fact, unfortunately, most textbooks also stop, right? They say, okay, good, right? We have a good model, but you don't stop here. You need to go further because these values can be misleading. Remember, guys, a model cannot be shown or proven to be correct or effective. That can only be disproved. So you have to look at all sorts of areas which may worry you. Go ahead.
One quick question on that cell there. You can scroll up a little to show that. So that one, it says print mean squared error, and then there's a function mean squared error. So where did that function come from?
Oh, we imported that. It's one of the functions built into the scikit-learn library.
Okay.
So,
And R2
yeah, let's go and see that whether it's true, where it is, since you ask.
It is standing on its own without having a reference.
Yeah. Do you see this line from the scikit-learn mean squared error? We have that, right? So thank you. Yes. So now it looks pretty good. And this is about string formatting, etc. You learn all of this, how to prettify strings, the output and so forth. So residual analysis, what is the residual? I use RI because your book tends to use RI. right? Otherwise, I would have used epsilon I. Remember in the lecture, I used epsilon I. Right? So this is it. And once again, guys, those of you who are, do you notice that the math is formatted as math and so on and so forth? This is because I am injecting in my markdown the LaTeX syntax everywhere. This sort of thing is very typical of the sort of LaTeX language. You don't have to know this. And if you can't write statements like this at this moment, obviously you don't have to worry about it. Right? So we will look the now there is an excellent library called Yellowbrick. Right? You can do it by hand, but it's much better to use a nice professional library. So I'm using the Yellowbrick, and in the Yellowbrick, I'm doing something called residual plot. So what is it doing? It is for every value of output, like y, you're trying to find what is the residual. All right, is like how much residual you see. Now, here is a rule. It will take you a while to absorb, and you do it both by making predictions on test data as well as trained data. Now, the interesting thing with residual is residual plots, if it, let's put it this way, if it doesn't make sense to you, it's a good thing. If you don't see a pattern, if you don't see any sort of noticeable pattern, if it just looks like mostly noise like this, it is a good thing. And also, as you go from left to right, in other words, for different values of y, do you see the spread of the residuals? Do you see that the spread of the residuals is more or less same, constant, right? There's not any significant variation. That is one thing to notice. When you have this, when residuals don't show, so what you're seeing is that the variance of residuals doesn't change for different values of y. Or the predicted value, it doesn't change y hat, right? So this has a lovely word. And that word I'll make you familiar with. The words is you have. Now I want one of you to try to pronounce this word. It's a lovely big word. Yes, homoscedasticity. Excellent. So, I'm reminded there is this story. Most of you, if you grew up here in this country, know about Mary Poppins. So she is trying to boost up make the kids feel confident. So she teaches them a word, to a big word so that they feel really good about it. And then the word is something like supercalifragilisticexpialidocious, right? And they all think, oh, good. So as we are learning data science, well, here is a big word for you, right? What it means is, it means exactly that when you don't see a variation in the variance itself, right? The variance doesn't change as you go from left to right. Other things, do you notice that if you look at this part of the plot, do you realize that it has sort of a bell shape, right? The errors, the residuals, the histogram is bell shaped. Most of the residuals are small. Some of the small amount of residuals are big, isn't it? Do you notice that more points are closer to this black line than away from the black line? As you go away from the black line, it becomes thinner and it becomes more and more sparse. That is what this histogram is showing. It is a good thing. When errors show a normal distribution, it is generally a good thing. Yes.
So when we split the sample, that was, we didn't do any judgment sampling in terms of splitting, right? Because
no, random sample, no, random split.
So why the error, if you look at the height of the residuals.
Oh, right.
Set and test
the reason is that the test set data is very small. I believe it's just 25%.
Okay.
That is why the histogram can't rise. I mean, it is not the frequency plot. There isn't enough test data. There's less test data than trained data. Trained data is almost twice or thrice as much.
Oh, that's just a frequency plot.
That's just a frequency.
It's not showing the magnetic.
Yeah, it's not scaled down. It's not scaled down. Yeah. It is not scaled down. Right. So that is it. Is a distribution. So I will draw some. Yes, go ahead.
Yeah. So we said like on the graph, we are looking for patterns and we don't see any pattern moving left to right, right? I mean,
yes.
So, I mean, if we find some pattern here in this example, we don't have, but let's say that we find a pattern, like, will we go again the steps like removing outliers from that pattern, trying to
No.
identify if there is a pattern?
Yeah. Okay. So if you see a pattern, then you will say something. Repeat after me. Oh, shucks, I need to do more work.
Okay.
Right?
Right assumption was found.
Right. So basically, it means that this is maybe a reasonable model, but there is a better model that you can do better than this. All right. That's all it means. So, well, let's play around with it. And you'll see it in the next data set. Exactly that we'll see. Huh? So now, so you have homoskedasticity here. But in the next one, you will see heteroskedasticity. So we now finally, everything looks good. R square looks good. Residual plots are lovely. No patterns in it. We are feeling pretty good about it, isn't it? Let's go ahead and you plot. One final thing you must always do, especially when data is low dimensional and you can visualize the predictions. Create new data, predict. Put the prediction line, the straight line, the hypothesis line, over the data and see how it looks. So this is a little bit of code. What I'm doing is I'm generating new code and then making predictions on the new code and plotting it. When I'm plotting it, I'm plotting the prediction line on top of the data. So when you do that, does the prediction line seem to agree with the data? Is it making a good representation of the data? It is, right? So now this is lovely. So we conclude that there are multiple indicators for this data set. We have multiple indicators that we have arrived at an effective model. The coefficient of determination is good, actually very good. The residuals exhibit homoskedasticity, right? And there are no patterns. Finally, the prediction plot, when superimposed over the data set, indicates a high degree of agreement. All three things, isn't it? At this moment, you have strong confidence that you have a nice, effective model, right? So take a minute, if you were doing this, take a minute and congratulate yourself on the successful data science journey. Because usually, while this sort of graph is very common in textbooks, in real life, you rarely see them. Linear relationships are not very common, but nearly linear relationships are much more common. And they are relationships that you can make linear through transformations and whatnot. And that's sort of the journey of evolution we'll go through, right? But for now, this is as good as it gets. You build this first model that you try just works. Are we together? So this is it. This was your first notebook. Any questions, guys? I hope, so this code, right, you can ignore the aesthetic aspect of it, but I hope you find, and it will take you a little bit of time to become familiar with the code, which means that you have a tremendous amount of homework, guys. Repeat this for the next 5 data sets. That is first, that's your homework. Pranjit, 1 second. Huh? And the second thing is that you have to start learning pandas, NumPy, a little bit of NumPy, etc. See, those are vast things, but you need a very tiny, like, from a bucket, you're just taking a cup full of water. Are we together? And that's all we need for our purposes for a very long time. And pick up other things, to go deeper on a need to do basis, need to learn basis, right? Start with simple things, start by getting a hang of this code, but really understand this code properly and begin to use it, and then go for that. Premjit.
On the last cell, I think from the code, can you show us how you superimpose?
See, here is a plot.
Yeah.
So I say, you see that I put a scatter plot. What does it do? It makes this nice salmon little bubbles, isn't it?
Okay.
But over the same plot, it's called axes actually in the line.
The second line was the
yeah, I superimposed that. Okay, that is it. So guys, do please pay attention to it. Oh, we are almost at 5 o'clock, right? So we are done with only one notebook. So remember, you'll be here till dark. That's right. Are we willing? The second notebook gets more interesting. You may say, all right, this was great. I got a good introduction to doing data science, but reality is more complex. Let's try something a little bit more complex and see what happens. Albert.
So I have some errors on the notebook. I can see everything, but so then the notebook is running on Anaconda. So what does that mean? Does it mean that I'm missing the library somewhere? On my
Yeah, you need to. For example, you may not have done pip install Yellowbrick.
Okay.
So remember, guys, when all of these libraries, whenever you see import this and it fails, it means you have to do pip install that. Right? Just go install those libraries. And please reach out to our TS. Just all you do is you can open a new cell, exclamation mark, pip install whatever, and run it. But do it only once, otherwise it will slow your notebook down. Right? So that is that, guys. Let's go now to dataset 2. Okay, in this we will learn another variation of linear regression, still linear, because in, believe it or not, a polynomial equation, if you add higher degree terms, a function of x and x function, also x squared term and x cubed term, it is still considered linear in the language of higher mathematics, basically, most of the time. Right? Non-linear is different. It was one of the things I was explaining. But okay, so one of the things that I will tell you is that whenever you see a bend in the data, right, you can see a bend, count the number of bends. And at some point, I'll explain in the theory section what it is. But, or maybe, well, today we don't seem to have enough time. Or I might as well do it properly. 1 second. Where is my writing pad? One note. Okay, guys, I think we all need a 5 minutes break. I can see people are going to the restroom, etc. Let's take a 10-minute break, actually, not 5, 10 minutes break. I'll see you guys after 10 minutes. So guys, here is a fundamental fact of algebra that you may have forgotten. Observe something very basic. This is a straight line, isn't it? I'm sorry, I don't know what happened to that. How many bends do you see in this? What is happening?
Using and just period.
No, I think it is gotten into some sort of update. No, it was updating itself, unfortunately. Touch off. Okay. So let's try again. All right. We'll go to the bottom here. Observe something. A straight line, something with one bend, I don't know, I'll make it like this. Something with two bends, right? And something with three bends, like this, right? And by the way, the bends could be any way. It could be like this, whatever, these curves. This equation is y is equal to beta naught plus beta 1x. It's an equation in linear in x. This is quadratic. Those of you who still remember your equations of parabola would remember that you need to go to the quadratic term. Are we together? If you try this out in the same way, beta 2 x squared plus x cubed, you will need at least a third degree. What do you conclude from this? So I'll just write it in order 1, order 2. That's not poly 1. I'll just use a poly 1, polynomial of degree 1. This is poly 2, poly 3. So this has how many bends? 1, 2, 3, 4. 3 bends. 3 bends means what? Poly 4. Do you see a pattern? Can you generalize from here? Right. So what happens is when people encountered the nonlinear relationships, one of the tricks they thought, okay, we won't write it in just x, but x squared and x cubed. We will add them as extra features. And we'll treat it as a linear regression model in 3 features or 4 features. One is x, one is x squared, one is x cubed, and so forth. And we'll still do linear regression. We'll apply linear regression to it, and it should work. Does this make sense, guys? By the way, if you want to prove this thing to yourself, it is a fundamental theorem of linear algebra, which says that a polynomial equation of degree n has how many roots? How many times does it cross the 0th axis? Right, a certain number of times. So this is where it all comes from. So I'll leave it as that. So now using this relationship, one may be tempted. Yeah, go ahead.
You have x and x. So x is a one feature and x squared is a other feature. And
Exactly.
Okay.
Yeah. So you're literally treating them as independent features and building a linear model in those additional features. Right.
And maybe it's a digress here. Just quick question, Asif. So the polynomial 4 looks like a trigonometric function. Do you deal with those things at all, or is it just we're going to go only to polynomials?
Yes, very good question. You will see that the data set 2 does seem reminiscent of a trigonometric function, sin x, isn't it?
Yes.
Right. So we will come to that too in a later lab. So there are many ways that we will solve this problem. Right. That is in particular nonlinear least squares. We'll do that.
Okay.
Solve
Thank
the
you.
same problem using other means. Right. So, but nice that you asked that question, actually. Now, coming back to that. So that's what we'll do. So what are the prerequisites for this lab? Of course, you must have done the lab 1 because notebook 1, I wouldn't be repeating the things here. What are our goals? Standard. We'll apply polynomial regression models now to make the prediction. At the end of it, from this lab, what do we expect to learn? I expect that you learn the importance of residual plots or residual analysis. And you will learn about heteroscedasticity and what it indicates. And polynomial, I have my typo here. Excuse me, a polynomial regression, you'll learn. Imports are the same. I don't want to repeat those. Load the data exactly the same way. All of those considerations remain the same. I'll skip over it. Missing values. It turns out data set 2 also has no missing values. Right? Pretty good. So missing value, we don't have to do any treatment. The point is moot. You can do pandas profiling, which we won't. You can look at the results of that. It is interesting. Right. And finally, let us now go plot this data using matplotlib. Exactly the same code. Do you notice that quite often the same code here is working just fine? The same code that I had before. Now, you look at this data, and the first thing that strikes you is it a linear relationship? No, there are 2 bends. 2 bends means what is the polynomial degree I need? 3, minimum 3 should get our job done. So let's try our luck. But suppose you don't do it, and this is what happens. See, guys, how many books? Look into the books. How often they talk? Some talk about a polynomial regressions. Most don't. Right. So it's one of the things that is very crucial, very useful, but often missed. So if you do a naive regression model, the same code, you split it into test and train data, build a regression model, and you realize that it is saying the intercept is this and slope is this. All right. You try to make the predictions from this, you do a residual analysis. When you do a residual analysis, the very first thing that strikes you is what? Do you see a pattern in the residuals? Very clearly, you see a pattern in the residuals, isn't it? The whole thing has a certain shape to it. So it has patterns to it, and therefore there should be alarm bells. Means there can be a better model. Surely what you're doing is not good. And if you persist on and try to impose the model on the predictions, you learn something actually. Look at this graph. What do you learn from this graph? Do you realize that the prediction model, if you believe that straight line is the right relationship, right? You build a model that is simpler than the ground truth, isn't it? Your hypothesis was simpler than the ground truth, that just a linear model would do. And what has the learning done? The machine has learned the best line that could possibly fit this data. Just pay attention to it and you can convince yourself there is no better line that you can fit to this data. Isn't it? Right? You can't think of any other straight line that will do better. And this is interesting. And this is the point that you have a model. So now some part of it is a reducible error. We can do better than that. We'll do that. So clearly, you see patterns in the residual and the predictions have very not as good fidelity with the actual data as you would wish. So let's try better. Can we fit a polynomial of degree 3? Yes, we can. So let's do that. Creating a polynomial of degree 3 is not hard, actually. Everything remains the same. The rest of the code remains the same. The only thing new feature is you bring in this polynomial features. You say how many degrees? 3 degrees. And by the way, play with it, guys. Go to 5 degrees and so on and so forth. See what happens. So now you create a data frame, x poly, which has x, x squared, x cube as 3 features. Are we together? 3 features. And then the rest of it is simple. You build a model here. You fit the model to the data. Then if you go polynomial expansion on the training data, you have to do the same thing on the test data before you make prediction, isn't it? Because the model is expecting 3 variables, 3 input arguments. So here we go. You make the prediction. And this code, guys, step through it. If any part of it looks hard, do reach out to us. But absorb it. Model.fit. It is the same code, R squared. So what does the coefficient of determination look now? 96% or 96.5%. What was it before? Before we did it? In the previous model, it was? No, it was 53%. So from 53%, we have gone to 96.5%. Huge improvement, isn't it? The previous model is marginally useful, somewhat useful, but it hasn't picked up, it hasn't sort of done as good a job as the second model. Let's look at the residual. So you're looking at the residual. Do you see a pattern in the residual? Now, lovely. So you have homoscedasticity here. Lovely. So then visualize the third part. Visualize the model predictions over the data. What do you say to this? Pretty good, right? So polynomial regression seems to be a very powerful tool. Use it judiciously. Do use it as often as you can. And this is all it is. Oh, by the way, there is a homework, but I have put it in the second data set. Your homework is analyze all the data sets that I have not analyzed or created the notebook for. Each of these data sets, trust me, guys, has a unique lesson to teach. Like, for example, this data set 2 had a lesson to teach. What was the lesson that it taught? Polynomial regressions, isn't it? And now I'll go to the third data set. This is it. Any questions? I hope this was simple by now. You notice that there's a certain familiarity to this thing by now, right? We are following a method systematically. And the method remains the same. But as we explore data, our findings change. What we see in them changes. And how, therefore, we treat them changes. Right? But keep your method more or less coherent there. The third data set.
A quick question. This is
Sorry, go ahead.
So the distribution, it doesn't seem completely normal. There are gaps in between. What does that mean for residuals?
Nisarg, I think it is Nisarg, you have 2 computers, or maybe you have a headset and a laptop separately attached. So we are getting echoes and I can't. So either you can put the question on the chat and I'll watch it, or you'll have to mute one of the machines. Would you like to try again?
Is this better?
Well, let me try. It's not actually, but we will all try to understand what you're
I think Asif, I got what he's asking. He's asking for linear, like the distribution has some gaps. Why exactly are those gaps? Meaning, am I right, Mr.?
you're looking at this, or you mean gaps here? Which plot are you looking for, Nisarg?
Yeah, that one.
Yeah, see, no, this is it. Gaps are okay because the data distribution itself, underlying data distribution. Come again? Oh, he has put it in the chat. Okay, excellent. Let me go to the chat and read what it is. What does it mean? Oh, what does it stand for? Yeah, so let me answer that. See, in what it means is, it turns out that the data has not been, the errors or the residuals are not uniformly spread. Sometimes it is the nature of the data. If you see pronounced patterns in the in that frequency plot, very obviously something's skewed or odd, then you worry, but generally you don't worry about this. No? You let it slide. I mean, you basically say this is harmless. All right. This does happen with real data sometimes. Does that answer your question, Mr.? I hope so. Okay, nice. So this is that, guys. So we learned about polynomial regression. I can't emphasize enough, guys. Use simple techniques to analyze your data before you bring in the big guns, right? Polynomial regression is just one couple of lines of extra effort over linear regression. Try it out, see if it works, right? What does it give you? Very often it does work. Now the third data set that I'm going to analyze, and the last for the day, because I can literally see tiredness on everybody's face here, is our third data set is the Runge phenomenon. By now you must say, wow, polynomial regression is really powerful. Now most nonlinear data, I can fit I can do polynomial regression and win. So the lesson you will learn today, that there are many reasons why polynomial regression does not always work. One of the reasons I'll show you in this lab, the second reason you will discover when you do the labs on your own, the remaining homeworks on your own. But it is a fact. See, if polynomial regression always worked for all nonlinear relationships, the rest of machine learning would have been redundant, isn't it? You did linear regression, polynomial regression, that's it. End of chapter, right? But it isn't that. The reason for that is, at least one of the reasons you'll learn today, but there is a deeper reason, which is that there are functions which can never be represented by a finite polynomial, right? Those functions are called, what are they called? Transcendental functions, transcendental functions. Those are marvelous things. Basic transcendentals are what people often in textbook call early transcendentals, are your sine, cosine, trigonometric functions, and your inverse trigonometric functions and all of that, and exponentials, e to the x and so forth, and logs and so forth. So these functions can never be represented as polynomials. If you try to represent it as polynomials, you will end up with infinitely many terms. So they have infinite polynomial expansions. So the word transcendental, they transcend the ability to be expressed as polynomials. Now, why are they important? Why? Who cares? Well, it turns out that transcendental functions are the fundamental language in which nature is written, right? If you were to put it more poetically, if we were to read the thoughts of God when he was creating the universe and the language in which he created the world, it would be in terms of transcendental functions. They're everywhere. You drop a pebble in the water, the ripples are your trigonometric functions, sine, cosine waves, right? You're approximately, right? But actually, the amplitudes are, I believe, if I'm right, yeah, they're Legendre polynomials, right? The beating of the drum has that same expression, right? Do you see? Close to the center of the ripple, the way you drop the pedal, the amplitudes are high, and then it gradually drops down, right? You have that. The atom itself, right? The modes of the atom, the SPDF, and so on and so forth. I'll leave it as a question for you, but you'll be surprised that that electron cloud itself follows a transcendental function distribution. Those are the modes of the transcendental function. So transcendental functions are everywhere. You look at the cable hanging, holding the Golden Bridge up, and you write the equation of that, it will be a transcendental function. Wherever you look, it's transcendental functions, right? In nature, and in artificial things, in engineering and medicine, in the body, everything is mostly. So what it means is that a lot of data that comes to you, the underlying generative forces are transcendental, expressed as transcendental functions, right? Which is why polynomials work. They are good approximation quite often, but they don't always work, because so often nature is written, or data, the forces that created the data, underneath it, the more appropriate models are models using rather exponential functions and complicated relationships, right? And those cannot be captured. Those nonlinearities cannot be captured by polynomials. That is one way. The other is actually something pretty simple and interesting. You see it. So in this, we take this data set. So outcome is we'll learn about the limitations of polynomial regression and a phenomenon called the Runge phenomenon. What is the Runge phenomenon? It is this. We'll take another data set now. This is data set 3. Pretty much the same analysis. Let's go straight to its visualization. Oh, here it is. Is this reminiscent of some curve that you are quite familiar with? Bell curve, right. It is actually this. So now let's try to do the standard analysis. If you try to build a linear model, obviously that would be a rather foolish effort. Your residuals would look like this. Practically a mirror image of your bell curve, like laterally inverted, and not laterally, horizontally inverted. Okay? Visualization of the prediction over the model. See, this is your prediction, the line, the best line that you could fit to this data is this line. Does it have any fidelity to your data? Almost none, right? And it shows up in the values that you get for R squared. Remember, I told you that your R squared can be worse than 0, right? Here is a situation. Basically, I've lost it, right? So that is that. Clearly, we need to do better. So you can then try polynomial regression. You say, well, just now I learned about polynomial regression. It is something very useful and I can use it. Let's do that. When you do that, degree 2, degree 3, degree 4, you can keep on going. And you'll realize that you have to go up to degree 7 or so to get, I mean, high degree. I'm not fixated at 7, you may say 6 or 8 or whatever, 9, whatever it is, a pretty high degree to get a good model. And the code is exactly the same, huh? Degree 7. When you do that, you get a pretty good model. But when you do the residual plot, that's when it comes as a shocker. You thought you had a good model, and yet, what do you see? There seems to be discernible pattern in the residuals, isn't it?
Mm.
And you say, oh shucks, what do I do now? Right? And this is it. Let's try to plot your model over the data. What do you notice? Actually, it's not a bad model. Depends upon what purpose you'll use it for. But do you notice this, what I call the dog's wagging tail at the end?
Mm.
Right? So at both sides, left and the right, you see these oscillations. Right? More formally, these are called oscillations. This is the fact that happens. When you try to fit an unnecessarily complicated polynomial curve, high degree polynomial curve to data, what will happen is in the edges, you'll start in the periphery, you'll start seeing this oscillations of the curve or the prediction model, right? Or more simply, I call it the wagging tail, right? On both sides, you have a wagging tail, right? So when you have this was actually the mathematician who discovered this and who proved that it will always be so is Runge. And you can learn more about it. There's a Wikipedia page, which is a little technical, but if you are curious, you can do. And he showed that it happens more than 100 years ago, right, in 1901. So that is all I'll say. So what it means is that polynomial regression is a powerful tool, and you will learn in machine learning that there is no silver bullet. Every tool has its strength and weakness, which is why the field is so rich and filled with such interesting ideas, because no one idea is so good, is a silver bullet. For every situation, something else works, right? So a bit of a historic note about how all of this started. You can read about it, the thing that I told you about, how it all started. At least, actually, it should be 1793, not 95, but be as it may. Okay, so I already also told you about exponential functions or transcendental functions. Sorry. Now, by the way, can you guess? You realize that the equation of the bell curve is e to the minus x square, right? At the top, numerator, setting mu sigmas out. It is basically e to the minus x square over 2, normalized way. So obviously, that's a transcendental function, right? So if you know your math, you would say, well, of course I expected it to not work. Isn't it? Right? But of course, that's hindsight. You don't really know. It could have worked, right? Because you don't really know whether this was a bell curve or not, right? Or what it was. But anyway, be as it may, high degree polynomials run the risk of Runge phenomenon when you model with them. And that concludes today's labs, guys. Was it useful?
Oh yeah, definitely.
Wonderful. Huh? So all these labs are already uploaded to your class portal. Please do download them, run them. And the first one, the correlation interactive visualization, do play around with it to get a sense. You may have noticed that the pace of the class has changed, right? This session was a little bit more in-depth and hands-on than the previous session. Now, I cannot emphasize enough, guys. Please, please, please form your projects. Do these labs, even if you form your team and you do the labs together, the rest of the homework, that too is fine, but do it. Because without doing it on your own, there is no learning, right? All that you have learned will fade out. And the best way to learn is social learning. You guys notice that around this room are all of these meeting rooms or conference rooms, right? Each of them is equipped with a state-of-the-art audio video system, large TVs, right? A table with power literally embedded and Ethernet embedded in them. Come sit here, form your groups, discuss, do your homeworks. You're most welcome to. But do it, guys. The social learning or doing things as a team is an integral part of the learning process. It makes you learn better because different minds think differently and approach a problem differently, right? So you get enriched by the other person's thinking process. So do form your teams quickly, do all the assignments, and that project that I gave, which was to find a couple of types of trees, and for each type of tree, go pick the leaves of that tree and measure the attributes, length and weight and color and so on and so forth, and create at least 200 data points. You will see why this will be very useful as you move forward, right? Please do that project, put some energy into that project. I want us to see, what is the outcome we are looking for from this workshop? I want you to come out as stellar data scientists. Right? As far as tabular data is concerned, you folks should be able to do exceptionally well in your analysis, good, high quality results, not run-of-the-mill results. That will come only if you practice. Right? So do practice, please. With that, I'll conclude the recording.